Okay, so it's my pleasure to give this talk today here about multimedia data processing and content sharing in the IoT and big data era. I'm Jiangchuan Liu from School of Computer Science, Simon Fraser University, Canada. And currently I'm leading the NetMedia lab at Simon Fraser University. We emphasize on multimedia data, communication, networking, together with the data intelligence. And we have 2 postdocs, 8 PhD students, and 4 master students currently. And in past, we have students and postdocs now working as assistant or associate professors in Canada, United States, Sweden, and also Hong Kong and mainland of China. Our research have been sponsored by the Canada NSERC, MITEX, CFI, and many other industry companies. So, as said that we are now in the IoT and big data era, conventional internet, no matter wireless or wired, is a network interconnecting end terminals for communications. But today's internet and the Internet of Things is way beyond the communications between peers. Rather, it has become a distributed data source and data processing engine, and we see the data coming from single source to multiple source and to cross source. And the network now is rather data-centric rather than communication-centric, okay? So in particular, we see the fast growth of multimedia data over the internet. It has always been a key contributor to the internet traffic. And say 2015 is around 70%, but nowadays it has become 82%. It is projected it will go to say 90% in the foreseeable future, okay? So we see 1 million minutes of video across the internet each second, and internet TV, particularly ultra high definition TV content, has seen fast growth, and not to mention AR, VR content in the past years, okay? So in the past almost 20 years, every 5 years, I basically wrote a survey about the multimedia content distribution over the internet, review the state of the art. So say the first one, 2003, we see that time internet is still a communication infrastructure. We focused on adaptive video multicast over the internet. And then 2008, we have these opportunities and challenges for peer-to-peer internet video broadcast. At that time, the storage has become abundant at edge nodes, so the peers can store the content and share content with others. And 2003, in celebration of the 22 decades of the internet video streaming and also the 2 decades of ACM6 multimedia, the community, we have another survey in ACM transactions on multimedia and communications and computing, and we see that time we have computation, okay, and in particular cloud computation has played an important role in multimedia data content processing. So from that time, then we think about what would be the next decade and beyond, including nowadays, and we see what are promised and what are expected. So from end device perspective, we have very weak devices. Even passive RFIDs at that time can start transmitting some of the audio and video content. And on the other hand, we have very powerful spectrum, powerful devices, in particular vehicles, in the other extreme, okay? And remotely, we have cloud with storage and data analytics. And then we have the communication infrastructure moving toward 5G and software-defined radio and networking. So 2008, we have another review invited by CCF about multimedia streaming around 30 years. Okay, that's also the year that back to a decade, we see the first release of Android and first lithium automobile and OpenFlow and the deployment of 4G and the initial 5G deployment. Then after 10 years, then all these kind of things have been widely used, and they have been the driving force of the next decade. So basically, now we see a convergence and integration of social, cloud, and mobile computing for multimedia content processing and distribution. And we see a tight integration and convergence of communication, storage, and computation. They are not separate anymore. Rather, they have been tightly integrated together to serve multimedia content. Okay. And in fact, in this year, we have another edition of the Fundamentals of Multimedia, this classical textbook. In the past 2 editions, it has been widely used as the undergraduate or graduate course for multimedia content processing and distribution worldwide. And the 3rd edition now is ready. And in particular, if you look at the content, the part 4 has big change. In the past, the part 4 in the 1st and 2nd edition was multimedia information sharing and retrieval. But now, in this edition, it becomes human-centric, interactive multimedia, involves social media, involves AR, VR, and also involves multimedia content analytics and analysis. Okay. So again, we can see the convergence of different technology, and we can see the importance of the human-centric computing and interaction in this new era of multimedia. So now let's follow this evolution view and introduce our view about multimedia content processing and distribution in the IoT and big data era, and also introduce some of our works. Now basically from individual to the crowd, and then from crowd-source to crowd intelligence, and then from fog cloud architecture to the edge cloud architecture toward the future. Okay. So if we look at in the past, say, almost 30 years, the multimedia protocol and system evolution, the earlier time mostly focused on the network architecture infrastructure and also the basic protocols for transmission. And in the encoding part, where it also has the evolution to starting from the disk storage and then for internet streaming. Okay. But if you look at the recent 15 years, it's more about high quality distribution to satisfy the human demand. And in particular, there are more and more interactions with end users. And of course, in the very near future, we will see the applications with IoTs and also intelligent vehicles. And the encoding part also follows this route. So for individuals, we have done a serious work in the past. For example, delay optimization in cloud gaming and choose for online auction for the cloud instance subletting in multimedia content, and also the multimedia content delivery from the with network function virtualization from energy perspective. Okay. And one work is about mobile-friendly HTTP for 360-degree video, and we try to enhance the dynamic viewport of mobile applications with screen scrolling, and in particular considering that mobile devices, the operation is mostly about screen scrolling, this kind of human interaction, rather than the traditional mouse move or text interactions. Okay. And also we have examined the relationship between mobility and latency, in particular in the high-speed railways, which is an extreme of the mobile application, and we're demystifying the relationship between network latency and mobility based on the data analysis. This kind of end-to-end analysis can give you an idea about what is the relationship between mobility and latency. Okay. And we also explore the multipass TCP together with multimedia content distribution. Okay. And in particular, the energy perspective. This is important for multimedia and mobile applications. And we also have done the multipass TCP as the underlying protocol for HTTP streaming, the MPTCP+, which tries to enhance adaptive HTTP video streaming over multipass, because we believe that in the future, with multiple passes available over the internet and with multiple air interfaces, multipass delivery is necessary and is useful for high-quality multimedia content distribution over wired and wireless networks. So these optimizations are mostly for individual content delivers. And now let's see if we move from individual to the cross-source, what would happen, okay? And example is livecast. It has evolved starting from the Twitch, from individuals to the crowd, and many broadcasters can deliver their content over the internet, and it has become a major player together with many other cross-sourced livecaster providers. And for example, in China, we have worked together with Yinke and Kuaishou to characterize the user behavior in mobile personal livecast. And by understanding their behaviors, we can optimize their interaction with the users. Okay, and in particular, we have seen a heterogeneity challenge. In the traditional multicast or broadcast environment over the internet or wireless networks, the users or the consumers of the content are highly heterogeneous, okay, and this creates a lot of challenge in multicast or broadcast environment, and people have done significant works in the past. But in the livecast environment or cross-source livecast environment, not only the consumers are heterogeneous, but more important, the broadcasters themselves are highly heterogeneous. They're distributed in different places. They're online at different times. Okay, their contents are quite different. Some are of high quality, as good as professional producers in the past, but many are not that good, and their network connections are quite different. So how can we accommodate this kind of heterogeneity? For both consumers and creators becomes a big challenge. Okay, and also it involves cloud computing nowadays. And involves fog computing, because many of the consumers and broadcasters are of good computing capability. So how can we make effective use of their computing capabilities so as cope with heterogeneous video contributors and viewers and with cloud and fog computing? And we have proposed a series of solutions for this. Okay, and then that's mostly for content distribution. And then how can we make effective use of the intelligence from this kind of cross-sourced content and the human interactions? Then that's another interesting work. Or basically, we try to do computing for communication. Okay. And from this, we know that we are in the so-called social era. And if we look at YouTube in the past, if we want to find some video, it's mostly based on search, okay, like in Google search. And then we have recommendation algorithms, which is still a hot topic in internet, okay, that recommended videos to us. However, more recently, we see more and more use of the social network to share and propagate the multimedia content. For example, over WeChat's video sharing, okay, or over Facebook and Twitter. Essentially, in Facebook, over 500 years of the videos are shared among the users, and in Twitter, every minute there are more than 700 videos shared. And this sharing, the coverage can be very wide because it quickly propagates among the friend relationships. But the coverage also depends on many of the factors, not only just the tag of the video or how good this video is. It often depends on whether you have a powerful relationship with others. For example, whether there's a big V there, okay, or whether it's related to some timely event. So this kind of propagation can lead to quite different video watching behaviors, and understand this becomes very important. As an advertiser, you can put target ads for specific videos and viewer demographics if you know whether a video can be popular or not, okay? And for a content producer and contributor, you can attract potential revenues through micropayment mechanisms if you know the propagation structure. And of course, from network and cloud service providers, you can adequately reserve computation, storage, and bandwidth resources to serve your customers, okay? So that said, you need to know the characteristics of video requests from online social networks and identify the video propagation patterns in online social networks and accordingly enhance the system by doing popularity prediction and also accordingly the resource provision. Okay, so we have designed this kind of forecast algorithm based on reinforcement learning, the social forecast algorithm. Okay, you have the initial video propagation pattern, and from that, over the time, we can learn the future propagation pattern, and this is a trade-off between the accuracy and age or the time duration. So we have shown there is an effective trade-off of this and achieve high quality prediction, and accordingly we can make decisions for network optimization and for micropayment for content. Okay, and not only this kind of propagation pattern can be used during human interaction, and actually many other useful information can be used, including text. Okay, for example, in Gamecast, this is a popular source of live cast applications. There are a lot of bullet conversations among the users. Okay, and this kind of interaction actually can give you a lot of information about what happened during Gamecast. Okay, and if you can automatically extract this kind of information, then again you can make good predictions in terms of resource, in terms of game progress. Okay, and say we can do topic extraction and prediction from this kind of bullet comments. And we have done this about the bottlenecks in community interaction, and we have done topic-aware view pattern prediction in cross-source live interactive streaming. And basically, we do data parsing for the bullets, and we extract topic through emoticon-aware topic model. And from that, we can learn whether, for example, the game just started, or the game has entered the second stage, or it's very crowded and very highlight part of the game, and accordingly perform network resource reservation or other actions. Okay, and not only this, we can also, based on this kind of information, to do first mile live cast with highlight prediction, so we know which part of the game scene is important than others, and this basically gives you the region of interest, so you can accordingly compress other parts while focusing on displaying this kind of important regions. Okay, and we can also predict the gaze tracking and find out the most important part of the video, because that's our region of interest. I just show you this example. So by using the specialized eye tracking device, then we will know the viewer's interest in the screen. Okay, that's the focus, and accordingly adjust the compression for the game scene. Okay, during broadcast. And we can also build the relationship between our eye gazing and the touch pattern, and find out the patterns to do prediction for game playing. And in the previous example, we have to use specialized gaze tracking devices, mostly from Tobii and Israel company, which is not cheap. Okay, and it's a very specialized device. And recently, we are able to do this with Huawei company with smartphones. Okay, just the off-the-shelf smartphones, and to do real gaze tracking. Okay, and we can achieve quite high accuracy and using state-of-the-art smartphones. Okay, and therefore we don't have to rely on specialized devices. We have also used this kind of gaze tracking for 300-degree video streaming, and because using this, we can do effective viewport prediction, which is a very hard task in the past. Okay, so that's the use of crowd intelligence, And in terms of the delivery architecture, we also see the trend from fog cloud to edge cloud. And in fact, the earlier time when we started the cloud gaming, we have seen there is a trend from the console to the cloud, okay? And then in particular the mobile cloud. And we have devised the first cloud gaming platform over the public cloud, in particular Amazon EC2, okay? And we then found that this kind of for cloud computing is not necessarily enough because, for example, for first-person shooter games, the delay threshold is less than 100 milliseconds, which is actually quite tight for the client and cloud interaction in state-of-the-art internet. And if you think about VR, the delay will be less than 20 milliseconds, and for AR, even less than 10 milliseconds. And the resolution is expected to not only high definition or UHD, but rather goes to 8 to 60K resolution. And all these are very challenging, okay? And in particular for the newer applications, like the location-based augmented reality starting from Pokemon Go, okay? And if we look at the internet, even with the fast pass, for example, Facebook's fast pass over the mainland of United States is still not enough, okay? In fact, with today's internet, if we look at the internet weather report, still many of the passes can go beyond 100 sometimes to 200 or even 300, 500 milliseconds, okay? And in this case, we have to necessarily incorporate edge computing with cloud computing, and edge computing based on distributed data centers, and edge computing for 5G, okay? In this case, we have done a series of works on cooperative edge catching and transcoding, and for example, cloud and edge collaborative transcoding for personal live cast, and video catching at network edge using multi-engine deep reinforcement learning, and to find out the best content to be cached, okay? And also, we have done the cloud edge collaboration to optimize the personalized quality of service and quality of experience, in particular for cloud interactive live cast. And we have this kind of deep reinforcement learning enhanced personalized QoE for edge-assisted crowdcast. And we also see that in edge computing, then because all the functions should be very light, and you cannot simply rely on virtual machines, which is quite heavy, then in this case, serverless becomes a useful tool, and in particular for modern video analytics, because most of the time, then there might be no event to analyze. But if it happens, then there is a serious event across multiple cameras, then you have to carefully analyze and add the instances to analyze this kind of content. And in this case, you have to automatically configure the pipelines and tuning the pipelines for serverless video processing. And we have Charm Seeker to do this kind of configuration automatically based on the historic data. And this is basically our edge and cloud collaboration for scalable video analytics. So we have a monitor monitors the cloud execution information and edge execution information. And from that, we have content-related matrix. We predict it and predict the cost expenditures or resource demand. And then we have the scheduler. Once there is online query, we devise the partitioning strategy between cloud and edge for serverless computing and scalable video analytics. Okay. And towards the future, as we said that there are two directions. One is even less powerful, but very promising. And the representative here is the backscatter communication, or typical example RFID. Okay, we have the excitation signal, and then it's backscattered by the tag, and then we can read it, and get the content. Okay, from this actually we can do a lot of useful things. For example, tracking the location and with fine-grained signal analysis. Okay, and this is touchless, and this is without power or without battery. Okay. And we can achieve very fine-grained tracking with RFID, much smaller, almost 1/10 of the previous studies. Okay, and we also use this kind of wireless signals to do health monitoring. Okay, for example, normal breath, or when you have pneumonia, those kind of special situations. Okay. And all these information provided to enhance the human and the system interaction. Okay. And also, we try to make the throughput higher and also compatible with other communication technologies. So the excitation signal does not necessarily to be dedicated RFID excitation signal, but can be any, for example, Bluetooth or Wi-Fi LoRa. Okay, and this has to be of a higher bandwidth, longer distance, because we are thinking about using it to deliver sound information and video information. Okay, say we have done high throughput and robust rate adaptation for backscatter networks, and we have devised the first special spectrum backscattering with commodity Wi-Fi in the world. Okay, that's in MOBISys 2018, and also in MOBICOM 2018 we have the world first multi-hop backscatter communication with commodity Wi-Fi, so that we can deliver content over multi-hop and batteryless. Okay, and it can avoid obstacles and reach the destination. And this is our X-Tandem.
X-Tandem is the first multi-hop backscatter system that can provide path diversity and robustness. Tags can do relay for each other and embed their information together in a single Wi-Fi packet. This prototype demonstrates a 2-hop backscatter system. With a size like a card, our tag prototype has FPGA-based modulation circuits and free pins to connect external IoT sensors. We can see the excitation signal on channel 1, the first hop signal on channel 7, and the second hop signal on channel 13.
And in this year's MOBISys will further demonstrate a scalable sensor mesh with distributed excitation. So the excitation not only comes from a single place, but can be distributed in the network so as to support multi-hop and mesh-based transmission and toward a fully scalable wireless sensor mesh. Okay, and without battery supply, and also the nodes there can be decodable with signals, not only just blindly forward signals as in the past. And also we demonstrate that energy can be harvested from sound and RF, and in particular with a sound over 70 dB, it's enough to support our sensing applications. And this 70 dB is not that high. In a busy street, you can easily approach this kind of sound level, and therefore it's widely applicable in the city's environment. Okay, and another spectrum, as we said, that is even more powerful and promising, that is a car, and we believe that this will be the next generation computing and communication platform, and from entertainment to automotive. Okay, and if you look at the modern car, it has 300 sensors, and not to mention the smart cars or electric cars, which has sometimes over 1,000 sensors, and it's equipped with 5G communication nowadays. So it's connected, social, and smart, like what we have seen in the past for advanced network architecture protocols, we now have ambient context sensing and front-end and back-end intelligence for the cars as well. And we see the convergence of cloud, social media, and communication storage computing for cars, modern cars as well, okay? So in this case, you are talking about heterogeneous connectivity, precise positioning, and on-device machine learning, okay? And again, there is a cloud edge architecture for the vehicles in different levels. For the vehicle itself, we may have embedded hardware for location computing and decision, which is less than 1 millisecond. The typical applications like assisted driving, auto driving. And at the network edge, with the support of 5G application communications, then we have local data, like the street level data processing, okay? And we have nearby vehicle-aware local decision, less than 10 milliseconds. And then on the cloud level, we have city-level data processing through the internet and toward smart transportation. And we have cross-source navigation, car trip sharing, and last-mile logistics and battery analysis, these kind of applications for modern cars. Okay? I just show you some examples we have done. And in the first case, we have seen in the past we can track the eyes or gaze tracking with a specialized tool or with our own designed smartphone solutions. And with the eye movement and wheel movement, if we can link them, then we will see what happened, predict whether there's any dangerous driving behavior, predict the driver's current situation, okay? And in this case, we can find out whether it's in cruise mode, whether in scan mode, navigation mode, and turning mode, okay? For example, if the user is doing some right shoulder check, okay? And during the turn, if not, we can provide necessary warnings. And of course, we can devise many other novel applications based on this kind of interaction of eye gaze tracking, okay? And we can also use the backscatter communication, particularly RFIDs, to do in-car activity sensing, okay? And in this case, this is non-intrusive, okay? And also, and much cheaper than other existing solutions. The challenge, however, is that the car's environment can be much more complicated than many other existing environment that we have studied for action or activity recognition with RFIDs or other wireless devices. It's a very compact space, okay, with a lot of obstacles, and also it's fully metal in the current cars, and they may block the inside wireless signals or having some other special effect. And then we have addressed this with raw data input, face processing, and activity segmentation, and time frequency transform. And from that, then we have this kind of domain discriminators so that we don't have to retrain the model in different cars. Rather, once we solve the problem in one car, then we can use multi-domain adaptation to transfer the knowledge to other cars and make effective use of the existing solutions. Okay. And also citywide, we have also done ride sharing as a service. In particular, our Car4Pack solution tries to use last mile parcel delivery through intelligent car trip sharing, and we analyzed the trip data in some major North American cities like Vancouver, Houston, and Miami, and from that we found out the best route for last mile parcel delivery in the era of connected and smart vehicles. Okay, and this starts from a landmark graph construction, and then travel cost estimation, and then task assignment, and it can provide good logistics with car sharing. So this is work with Module, a leading open platform with connected cars in North America. Okay, so that's some of our recent works, and we found that they are very interesting, and they explore the data in the modern cars and modern human-centric interactive multimedia applications. we hope that in the near future we can find more interesting applications and more advanced tools to further enhance them. And that's basically my presentation. And if you have any question, please feel free to ask me. Okay, thank you.
Respected experts, scholars, colleagues and students, my name is Zhenyu Zhou from North China Electric Power University. It is my pleasure to give a speech in EAI International Conference on Mobile Networks and Management, and I have learned a lot from this wonderful conference. The topic I would like to share with you is Ubiquitous Intelligent Power Internet of Things, Background, Applications, Key Technologies and Challenges. First, I would like to introduce the background of Ubiquitous Intelligent PIoT. Power grid is essential for national economy and energy security. The development of smart grid plays an important role in China's energy policy. The construction skill of China's power grid has ranked first in the world. By the end of 2018, the length of 35 kilowatts and above transmission lines had reached 1.892 million kilometers. The national electricity consumption had reached 6.9 trillion kilowatt-hour, and the electricity consumption per capita had reached 4,945 kilowatt-hour. China ranks first in terms of installed power generation capacity, power consumption, and renewable power generation capacity. For example, Changji Guquan 1,100 kilowatt UHVDC ultra-high voltage direct current transmission project has successfully crossed the Changjiang River and can deliver 66 billion kilowatt-hour of electricity to East China every year. A bidirectional high-speed communication network is essential to the energy supply-demand balance, as well as safe and stable operation of power grid. PIoT is an industrial-grade IoT applied to power grid, which realizes the interconnection of people, machine, and things in all aspects of power systems, and improves the intelligence level of power grids. State Grid Corporation of China and China Southern Power Grid put forward the concept of ubiquitous PIoT and transparent grid, respectively. Ubiquitous PIoT aims to provide communication channels for the power grid by leveraging the advanced information and communication technologies such as big data, cloud computing, mobile internet, IoT, and AI. It possesses the characteristics of comprehensive state sensing, efficient information processing, as well as convenient and flexible application. Transparent grid aims to realize a visible, knowable, and controllable power grid by installing small and micro smart sensors, making the information transparent in every aspect of power system, such as power supply, device state, network, and trading. Strong smart grid and ubiquitous PIoT together lay the foundation for the energy internet in the power system. Smart grid carries power flow and focuses on the generation and transmission side of the power system, such as the construction of renewable energy and ultra-high voltage projects. Ubiquitous PIoT carries data flow and focuses on the demand side to better satisfy the various service requirements of users. These two technologies complement each other and provide a powerful supporting platform for the energy internet, which integrates energy flow, service flow, and data flow. Different from the traditional infrastructure represented by railways, highways, and airports, the new infrastructure of China, the digital infrastructure, will assist in the upgrading the emerging technological industry with less resource consumption and environmental pollution. The Chinese new infrastructure projects focus on 7 areas, that is, 5G networks, industrial internet, intercity transportation and inner-city rail systems, data centers, artificial intelligence, ultra-high voltage, and new energy vehicle charging stations, involving multiple major industries such as communications and power. In 2020, the investment in the construction of new energy vehicle charging stations will reach 3.9 billion yuan, around $563 million. SGCC plans to invest 181.1 billion yuan, around $26 billion in the UHV project construction in 2020. CSG is also accelerating the construction of UHV and other new infrastructure projects, such as Kunliulong Direct Current Transmission Line Project, Yunnan-Guizhou Interconnection Channel Project. As the representative of new infrastructure projects, 5G network investment is expected to reach 1.2 trillion yuan, around $173 billion by 2025 in China. The cumulative investment of 5G and related industrial sectors will exceed 3.5 trillion yuan, around $505 billion. It can also support the development of technological industries such as AI, as well as vertical industries including smart grids and new energy. By April 2020, the number of 5G base stations in China has already reached 240,000, which is expected to reach 600,000 by the end of 2020. Simultaneously, Chinese telecommunication operators have finished the tests of the commercial 5G SA core network equipment and system. The advantages of resource isolation and high-speed services make the paradigm shift from the 2C market to the 2B market better, which promotes the application of 5G in vertical industries such as smart grids. Edge computing technology has also been applied to the power grid granularly. SGCC and Huawei jointly released a smart integrated energy service IoT solution, which utilizes a cloud network edge terminal core architecture. They also developed an energy cloud edge router with Huawei Edge Computing Core for the edge layer to improve energy efficiency. The megawatt-level energy storage plus virtual substation project based on edge computing has entered the installation and commissioning phase. In addition, the Ministry of Industry and Information Technology of China has issued the 5G plus Industrial Internet project to further promote the integration of 5G and Industrial Internet and boost the key 5G technology breakthroughs for Industrial Internet. In the field of 5G plus power applications, 500 kW Guandu substation has realized the overall coverage of 5G test stations, which verifies the large bandwidth service characteristics and high reliability of 5G networks in high electromagnetic and complex environments. 5G accelerates the construction of PIoT from the aspects of Internet of Everything, precise control and mass measurement. In terms of real-time data collection, 5G high-speed technology can support the transmission of massive data. In terms of demand response, 5G low-latency technology can timely respond to various changes in the system and realize millisecond precise control of power services. In terms of grid operation state monitoring, 5G communication technology can provide strong support for real-time perception of the operation states in the transmission and distribution grids. 5G will further boost the PLT construction, comprehensively improve the service level of the power grid, and expand new services. In the next part, I would like to introduce the main application scenarios and services of the ubiquitous intelligent PIoT. In 2019, China's electricity generation increased to 7.3 trillion kilowatt-hour, accounting for more than a quarter of the world's total generation, which equivalents to the total amount of the United States, Russia, and Japan. Moreover, the installed capacity of electric power generation in China will reach 2.13 billion kilowatts by 2020, ranking first in the world. In power transmission, the transmission line in Changji Guquan ultra-high voltage direct current transmission project traverses for a total distance of 3,324 kilometers, which covers the world's longest transmission distance. In power transformation, the highest substation was built in Makam County, Tibet, at the altitude of 4.3 kilometers. In power distribution, the transmission and distribution capacity of high voltage distribution grid had reached 3.25 billion kilowatt-ampere, and the length of the lines had reached 5.05 million kilometers. In power utilization, 503 million meters will be installed throughout the country by 2020, making China the country with the largest number of smart electric meters. Since the COVID-19 outbreak, grid companies respond quickly and take measures to effectively ensure power supply and actively contribute to the epidemic prevention and control. The left picture shows the staffs in the dispatch center who were ensuring energy supply in Wuhan. The middle picture shows the construction staffs in the mobile captain hospitals of Yangtze River Demonstration District, who has been working continuously for 15 hours. The right picture shows the power construction project in the Huoshenshan Hospital, where the electricity supply work was completed on the early morning of February the 1st. In the power industry, some new infrastructure projects have been started to provide more job opportunities, including North Shanxi Hubei UHVDC project and the Kunliulong direct current transmission line project. Besides, grid companies reduced electricity bills as required by the government. This will relieve the burden on enterprises who contribute to epidemic prevention and control. The State Council of China has issued the document, the Ministry of Industry and Information Technologies Circular on Accelerating 5G Development. On March 2020, the document points out that China should accelerate 5G network construction, open public facilities such as electricity sharing and base station sites, guarantee electricity and spectrum, adjust the use plan of 700 MHz spectrum, and the use plan of 5G millimeter wave frequency, as well as carry out the design and research on the dedicated spectrum for 5G industry. PIoT is widely used in daily life, such as time-of-use electricity price, online payment, smart home control system, and photovoltaic poverty alleviation. Under time-of-use rates, differentiated electricity prices are adopted based on peak and non-peak periods of electricity usage. Residents can flexibly adjust the weight of electricity consumption according to their own demands. The real-time payment function of smart meter can support consumers to pay online. Thereby, it can avoid the inconvenience caused by payment at the business hall. Residents can use the smart home control system to perform real-time and remote control of smart home appliances, such as air conditioners and water heaters. Photovoltaic poverty alleviation is one of the efficient ways for targeted poverty alleviation. Through installing photovoltaic panels on house roofs and agricultural greenhouses in poor areas, each household becomes a solar power station. In addition to the user's own usage, the obtained electric energy can also be sold to grid companies. To ensure the security and stability of power grid, the PIoT realizes real-time monitoring on all aspects of power generation, transmission, transformation, distribution, and utilization. Furthermore, it provides a variety of comprehensive energy services, such as smart energy service, distributed clean energy service, electric vehicle charging and service, and customized power service. For the 2022 Beijing Winter Olympics, SGCC plans to carry out a test and demonstration project of Zhang flexible DC power grid and 25 power grid projects, which enables the power supply reliability in venues to reach 6.9 and realize 100 green power supply. A highlight of the power grid projects in the 2022 Beijing Winter Olympics is intelligence. To solve the last-mile communication problem, the Olympic venues will be fully covered by 5G signals through installing 5G base stations in substations and erecting 5G antennas on existing transmission line towers. It can meet the communication demands of various services, such as high-definition video monitoring, real-time load monitoring, and intelligent inspection. In addition, the power grid projects are of great significance for meeting the power needs of Winter Olympic venues and promoting clean energy consumption and smart energy service. In the 3G and 4G era, precise real-time control cannot be achieved due to serious network delay, weak information security protection, and low network capacity. In comparison, 5G technology has the advantages of low delay, high reliability, mass connection, and high security, which can empower the construction of ubiquitous intelligent PIoT. According to typical application scenarios, PIoT services can be classified into three types, that is, control service, monitoring service, and mobile service. The control service includes intelligent distributed power distribution automation, precise load control, and distributed energy scheduling. The monitoring service includes advanced metering, integrated video monitoring. The mobile service includes intelligent inspection, mobile set construction operation control, and comprehensive application of self-organized network in emergency sense. Next, I would like to introduce the key technologies and challenges. The figure shows the ubiquitous PLT architecture proposed by SGCC in the Ubiquitous Power Internet of Things construction outline, which includes the perception layer, network layer, platform layer, and application layer. The perception layer collects information through various terminals such as monitoring devices and sensors, as well as performs signal processing by edge computing and other technologies. Its main construction goal is to provide standardized and unified terminal access, as well as resource sharing. The network layer receives the data and information from the perception layer and transmits them to the platform layer through the existing Internet and mobile communication networks. Its main construction goal is to promote the construction of various private networks for power grids and provide deep coverage as well as wide connection. As a full-service unified data center and IoT management center, the platform layer can solve the issues of data storage, usage, as well as security and privacy protection. Its main construction goal is to build an integrated SGCC cloud platform to realize the safe and open sharing of massive data. The application layer receives information from the platform layer as well as performs processing and decision-making. Simultaneously, it can feed back information to the perception layer to control the monitoring terminals and provide users with differentiated services. The main construction goal is to realize platform service sharing and support intelligent operation of core services. In the PLT, mobile service mainly includes robot inspection of substation, mobile set construction operation control, power emergency communication, UAV transmission line inspection, AR intelligent power inspection, and intelligent warehouse management. Taking the power emergency communication as an example, emergency communications vehicles at the central hub need to be equipped with large bandwidth devices such as UAVs and onboard cameras, and feed back the collected high-definition video information for comprehensive decision-making in real time. To avoid video congestion, the transmission rate of an emergency communication vehicle needs to reach 500 to 100 million bits per second, and the latency is less than 200 milliseconds. With the continuous growing demands on definition and real-time backhaul, the large bandwidth and millisecond-level delay requirements of mobile service need more reliable wireless communication technologies. In 5G communications, the related technologies of eMBB application scenarios can be utilized to meet the requirements of mobile service. Massive MIMO and beamforming technologies can effectively improve spectral efficiency, energy efficiency, and network capacity while reducing interference. Taking the UAV inspection as an example, the high-altitude flying UAV is hardly covered by existing base stations. Simultaneously, it is necessary to return high-definition video in real time to ensure the security of power transmission lines and power devices. 5G massive MIMO technology employs more antennas and introduces vertical dimension airspace on the basis of the original horizontal dimension to expand coverage, which can effectively utilize spectrum resources. Meanwhile, beamforming is adopted to adjust the parameters of each antenna and improve signal strength while avoiding interference among beams, which meets the requirements of UAV inspection service in terms of coverage, transmission rate, and latency. The monitoring services in the PLT mainly include low-voltage centralized meter reading, advanced metering infrastructure, distribution transformer monitoring, power distribution, room monitoring, state monitoring of power distribution devices, energy storage station monitoring, as well as smart grid video applications for inside and outside scenarios of the station. In the future, the monitoring objects will become multimedia and the content of monitoring service will be comprehensive. In addition, the monitoring frequency will tend to be quasi real-time and the fashion will evolve from one-way collection to two-way interactions. The data transmission of monitoring service is small-scale and low frequency, showing the characteristics of large uplink data traffic and small downlink data traffic. The conventional communication methods mainly include wireless networks and optical fiber communications, while various user terminals adopt centralized transmission modes. The rigorous service demand and the surge in the number of terminals will improve the requirements for wide coverage and mass connection in the communication network to realize real-time uploading of information and data collected by the terminal. In 5G communications, related technologies of MMTC application scenarios can be utilized to meet the requirements of monitoring service. With the simultaneous access of massive sensor terminals, the traditional wireless access network faces the challenges of access congestion, collisions, and high signaling overhead. To solve these problems mentioned above, the base station can allocate spectrum resources for each sensor terminal by utilizing fast uplink ground technology. In other words, the BS completes the uplink ground before the terminal sends scheduling requests to reduce the signaling overhead and access delay. To maximize the network's throughput in the information uncertainty scenario, the BS firstly predicts the active state of terminals. Then, by utilizing the steeping UCB algorithm of reinforcement learning, decisions are made based on the values of empirical estimation and the permission for uplink are distributed, which greatly improves the access success probability of the terminals, meets the large-scale access demand of the massive terminals, and ensures the reliable data transmission. In the power grid, the control services such as intelligent distributed power distribution automation, precise load control, and distributed energy scheduling have rigid requirements for latency and reliability. The latency is required to be millisecond level, and the reliability needs to reach 5.9. Based on URLLC, the accuracy of fault prediction in distribution lines can reach millisecond level, which greatly improves the reliability of distribution network. By realizing the millisecond level service response of interruptible load within users, the precise load control service is effectively guaranteed, and the coordination and adaptation ability of power supply side and terminal load side can be improved. The functions of voltage and reactive power control, islanding detection, dispatching, and coordinated control are realized to ensure the reliability of distributed energy supply. The end-to-end delay of traditional 4G network is about 50 to 100 milliseconds, and the ideal delay can only reach about 40 milliseconds under light load condition, which cannot meet the millisecond delay requirements of power grid control service. Meanwhile, all services of 4G network operated in the same network, in which the requirements of critical service isolation in power grid cannot be guaranteed. 5G network slicing technology divides a physical network into several end-to-end virtual networks, according to the service requirements of power grid. The logically independent network resources are divided, and the functions are customized as needed to meet the communication requirements of URLLC control services, and the slices are isolated from each other, which can realize secure service isolation. Simultaneously, by sharing the same infrastructure among different networks, automatic deployment and operation as well as cost saving are achieved. The multi-slice design and management architecture of smart grid is shown in the figure. The information collection slices, the distribution automation slices, and the precise load control slices are operated separately to meet the technical specification requirements of different service scenarios. At present, Huawei, China Telecom, and SGCC have jointly completed the world's first 5G IC electricity slice test based on the latest 3GPP standard. In 2017, we proposed a software-defined PLT architecture based on SDN and NFV technologies, which was published in IEEE Communication magazine. The network slicing orchestration is optimized based on the service requirements of different attributes such as generation, dispatching, differential protection, operation monitoring, and advanced metering. The gap between constraints and actual performance of reliability and delay is defined as a feedback signal. Based on the closed-loop feedback control, the dynamic adjustment of different virtual networks can realize the customization and the flexible adaptation of resource allocation. In traditional cloud computing network architecture, both the data analysis and device control lay on the cloud, which not only lead to various defects such as insufficient data security, network delay or interruption, but also cannot meet the communication requirements of low delay, high reliability, and high security of control service in the power grid. Mobile edge computing plays an important role in boosting the PLT construction, which has the capabilities of independent network, data acquisition, storage, and analysis, and breaks through the limitations of the network environment to a certain extent. MEC provides an extensible path which allows the combination of power grid device and edge data center to expand the computing power. The figure shows edge computing-based structure of grid energy management. At present, SGCC is exploring the construction and commercial operation of edge computing data stations and has completed 10 pilot projects. Due to the coupling among energy resource, reliability, and delay constraints, the system states in different time slots are coupled with each other. The environmental static optimization approaches are no longer applicable. To solve this problem, we propose a learning-based context-aware task offloading approach for edge computing-empowered PIoT approach, which was published in IEEE Internet of Things journal. The learning parameters are dynamically adjusted in an outline fashion by utilizing the context information, which greatly improves the performance of reliability and delay. Compared with traditional UCB1 algorithm, the queue backlog can be reduced by 69.39%, and service reliability is also greatly improved. Finally, I would like to summarize and outline the future directions. The development of PIoT is essential to realize the energy internet. 5G can support ultra-reliable and low-latency communication, massive device access, high-speed data transmission. It is necessary to develop and promote the application of 5G, 6G, and other advanced technologies in the PIoT. Moreover, the intelligent and sustainable evolution of power grid can be further promoted, and the industry implementation of ubiquitous intelligent PIoT can be boosted. Artificial intelligence-based PIoT is a hot research direction in the future. The intelligence mainly refers to accurate, dynamic adaptation and autonomous decision-making. The construction of PIoT can also drive the development of upstream and downstream enterprises of industrial chain. It is necessary to promote the ecological construction of energy internet and transform the traditional power industry into an integrated energy service industry. In order to realize the great connection of renewable energies such as desert solar power and offshore wind power, a large number of power infrastructures are distributed in remote areas. It is urgent to construct a three-dimensional heterogeneous PIoT communication network to promote the integration of complementary satellites, UAVs, and ground base stations. It can provide a communication network of large-scale coverage and flexible deployment. Thank you very much for your listening. Please do not hesitate to comment.
Hello, my name is Cao Tenfei, a graduate student from Hefei University of Technology, China. I'm pleased to have the opportunity to present this presentation at the online conference of EAI MONAMI 2020. The paper I will be presentation today is titled Throughput Optimal Uplink Scheduling in Heterogeneous PLC and LTE Communication for Delay-Aware Smart Grid Applications. My presentation is in 4 parts. In the first part, I will introduce the motivation of this paper. Smart Grid, also known as Grid 2, it is built on the basis of an integrated high-speed two-way communication network through advanced technology to achieve a reliable, safe, economic, and efficient power grid. It is the basic model of next generation of global grid. Power communication technology is important to smart grid. There are 2 ways of communication. One is wired communication. The other is wireless communication. Wired communication includes power line communication, optical fiber, Ethernet, and so on. Wireless communication includes Wi-Fi, Zigbee, TLE, 5G, and so on. With the promotion of distributed generation, consumers have begun to experience the advantages in generating part of the electricity. The principle of distributed generation is to achieve the goal of efficient, economic, and stable power generation in the distribution network system through direct setting or focusing on the power generation equipment near the load. DG is considered to be a form of diversified power generation. The relationships in DG can be applied to the data communication infrastructure to combine the correct cadency for critical and necessary data communication paths. This is the so-called hybrid communication system. Heterogeneous communication is an effective way to meet the needs of future communication service by using the existing multiple communication ways. It can give full play to advantages of various communication systems. The second part, I will introduce the related work in heterogeneous communication. At present, search on heterogeneous communication is still limited, mainly focusing on heterogeneous wireless communication. In the wireless heterogeneous network, different places of wireless networks are connected to the core network through the gateway. They connected to the internet and finally integrated into a whole. The first method combined PLC and wireless communication in smart grid data transmission was developed by Leonardo. This article analyzed the advantages of a hybrid system over non-hybrid system. then it only compared the achievable data rates of hybrid power line wireless channel model and hybrid power line wireless single relay channel model. There is no in-depth study on other performance of this system. So, introducing the above study, I will introduce how a proposed system optimizes the above problems. Our system is divided into 4 parts. They are frame, throughput model, and solution. This is the structure of our system. It consists of 3 parts: N types of sensors, intelligent grid multi-interface, heterogeneous communication platforms, and main stations. This is a data buffer in the PLC model, and it is used to temporarily store the transmitted data. In the buffer, the data are transmitted in line, according to the principle of first in, first out. The data buffer will affect the transmission delay of the data. We assume that the transmission data rate RPLC is consistent. The cycle time for data transmission in PLC cannot exceed the system delay requirements. In the LTE part, the data transmission model is the space-time multiplexing model of oscillational frequency division multiple access. We assume that the wireless transmission results block is limited for a period of time, and the results block consumed by wireless transmission data during results allocation cannot assist this fixed value. At the same time, packet loss of data will occur during wireless transmission, resulting in data transmission failure. In PLC model, the depth of the carrying data buffer is equal to the depth of the data if the data buffer at the previous moment plus the amount of incoming data minus the amount of data transmitted, and we use M to present. D is the data size, X is the variable to be served. We use T to present the time in the data buffer, and RPLC is transmission rate of the PLC. In LTE model, bit error rate is associated with SNR threshold and average SNR threshold. Then we propose a throughput model of a heterogeneous platform. It considers the bit error rate, the data volume of PLC and LTE. Then PB is the bit error rate. In our system, there are some constraints. First, the total time for data transmission by wire cannot exceed the delay requirements T. Second, the bit error rate of data transmitted wireless cannot exceed the required bit error rate of data, and P indicates the successful receiving rate of the data transmitted varies. Then, the number of resource blocks consumed by the data transmitted varies. Variously cannot exist the number of various transmission resource block Y, and R is the transmission of rate of the LTE resource blocks. Finally, a packet can only be transmitted in either a wired or wireless model. Also, we proved that the problem is solvable by formula deviation. Then we use throughput scheduling optimization algorithm to solve the problem. In other words, input perspective, bit error rate, and time in buffer information. Max the TP use throughput scheduling optimization algorithm to get X variables can represent the mode of transmission we need. Next part is the performance evaluation of the system. This is the simulation parameters to evaluate our proposed algorithm. We compare the single PLC LTE algorithm with the greedy algorithm with different D. We use D to represent the average amount of data sampled per second by the sensor. This graph shows you the throughput at different times. As you can see, at the same time, the throughput of our algorithm is the largest. And this graph shows that the buffer dips at different times. You can see the buffer dips of our algorithm at different times is more stable than that of greedy algorithm and single PLC. This is a comparison of the packet loss rate at different sampling time. It can be seen that our algorithm can reasonably schedule data to the PLC, so our algorithm can achieve better results in terms of packet loss rate. Well, that is about it for now. In this paper, we propose a heterogeneous PLC LTE uplink transmission scheduling method. Then we covered the allocation scheme into online programming and using the branch and bound method to find a 0-1 integrated solution. Finally, we compared the performance of our method with other typical solutions. The numerical experimental results show that our algorithm can establish the buffer dips and achieve a lower packet loss rate while maintaining maximal system throughput. This is the reference in this presentation. Finally,
That's all my presentation. Thank you all for your patience.
Hello everyone, I am one of the authors of this work, Zhou from Zhejiang University, Hangzhou, China. and I'm honored to get the opportunity to introduce our work, Distributed Spectrum and Power Allocation for D2D-U Networks to everyone here. I will first introduce the background of the D2D-U system as well as the problem we want to solve. Then, I will briefly talk about the contribution of this article. Next, the system model will be explained, including the specific Wi-Fi traffic load definition, the optimization model, the price-based model, and how to achieve the balance among different D2D-U users. Then, distributed learning-based method is the focus part I want to talk about, especially the loss function for unsupervised learning to adjust the price of the channel. Simulation results, conclusions, and prospects are arranged at the end part. So let's first talk about D2D-U. Maybe you have heard D2D before, device-to-device communications. It allows devices to transmit data with each other without the relay of base station. Then what's D2D-U? Here U means unlicensed bands. The spectrum mainly serves for Wi-Fi system. As D2D users using licensed spectrum for transmission may cause heavy interference to the cellular users. D2D-U can be utilized to relieve the spectrum shortage and the expense on unlicensed bands. So, while reusing unlicensed spectrum, the performance of Wi-Fi users should be considered, and one more factor we take into account is the fairness among D2D-U users themselves. I will give a detailed introduction later. Same with LTE-U proposed before. DCM and LBT mechanisms are utilized for D2D-U users to access unlicensed channels. LBT is similar with CSMA. The device will first perceive the channel and then generate a backup window. DCM may be easier to understand. The unlicensed channel will be divided into two parts, and one called on period is for D2D users, and the other called off period is for Wi-Fi users to transmit data. Here the DCM-based method is applied in our work. These articles give more detailed analysis to these two mechanisms. Here is a brief summary of the contribution of this article. A DCM-based channel access model is built for the D2D-U networks to share the unlicensed spectrum with Wi-Fi networks. And a novel traffic load on the unlicensed channel is defined. To balance the traffic load and spectrum efficiency of D2D-U pairs while ensuring the fairness, a price-based model is defined, and an online trained neural network with a specific loss function is applied to derive the price at each D2D-U pair adaptively. Finally, the centralized optimal solution is presented for comparison, and the simulation results are provided to verify the effectiveness of the scheme and the theoretical analysis. This picture appears again. The details of system model are shown, where there are n D2D-U links from D0 to Dn-1 transmitting with Wi-Fi users on the unlicensed channels. The number of accessible unlicensed channels is m from U0 to Un-1, and the traffic loads are defined as Lu and Ld respectively. What we want to solve is to maximize the throughput of D2D-U users while ensuring fair transmission among D2D-U users, and also the fairness of Wi-Fi users. Here, MBS will provide part of the training information for D2D-U users. I will explain it in the later part. As mentioned before, to ensuring the fairness of Wi-Fi system, we need to have a clear definition of the Wi-Fi traffic load. Here we assume that the load of Wi-Fi users is saturated. Then the Wi-Fi traffic load is decided by the number of Wi-Fi users in the channel. The first figure is the relation between the number of Wi-Fi users and the total throughput of them. Here G is the size of backoff contention window, and M is the maximum backoff contention stage. G and M are fixed in the physical layer according to AO 2.11. we can find that the impact of the number of Wi-Fi users on the throughput of the Wi-Fi system is nonlinear, and D2D links cannot directly determine the duration of on period in DCM based on the number of Wi-Fi users. Because the total throughput first increases and then decreases, we use the average throughput of Wi-Fi users at the maximum throughput point to define the Wi-Fi traffic load. Specifically, we use RK max here to be the value of maximum throughput on unlicensed channel UK, and NK-max here to be the number of Wi-Fi users corresponding to RK-max. Then we can get RK-hat-max is equal to RK-max divided by NK-max. It's the average throughput of Wi-Fi users at the maximum throughput. So here we consider RK-hat-max as the basic throughput guarantee, which means that when D2D-U pairs reuse the unlicensed channel or use unlicensed channels based on DCM mechanism, the average throughput of Wi-Fi users should not be less than this value. Look at the right figure. The red point is the position of RK-hat-max, and the orange point is the real throughput based on the Wi-Fi users' numbers. When the orange point is on the left of the red one, it means that the channel is accessible for D2D-U users. And when the orange point is equal or on the right of the red one, the channel is already overloaded for D2D users. As for the number of Wi-Fi users, some methods based on Kalman filter have achieved accurate results. Based on this, the value of Wi-Fi traffic load LKU can be calculated. Here, theta IK is the duration of on period for D2D users DI on the unlicensed channel UK. Okay, the problem mentioned before will be built as an optimization problem. Here, Ri is the achievable data rates of D2D-U user DI on unlicensed spectrum. Here, Bj is the bandwidth of the unlicensed channel Uj. Hij is the channel power gain of D2D-U pair Di on Uj. And Pij is the transmission power of Di on Uj. And N0 is the noise power spectrum on unlicensed channel. Here, theta ij mentioned before is the on period used by Di on Uj. Since we are designing a distributed scheme, so all D2D-U users will build an optimization problem for solutions themselves. Take Di as an example. So the goal of the optimization problem for Di is to maximize its own throughput Ri, and the constraints including Wi-Fi fairness, the power constraint, and especially the price constraint. Here, Cij is a price corresponding to the unlicensed channel Uj for the D2D-U link Di, and the C is the total money which each D2D-U link holds. It can be understood that each D2D-U user has the same asset, but the prices of the channels are different for different users. Herein, one important key to solve the problem is to find the price Cij. If Cij is known, the above problem is a convex optimization problem, and the optimal solution can be obtained based on the Lagrangian multiplier method. In fact, it takes the step of parameter substitution to convert the problem into a convex problem. For details, please refer to our paper. Then, how do these price parameters control the fairness of D2D-U users? Obviously, for D2D-U users with higher traffic load, the channel price should be cheaper. And for D2D-U users with better transmission conditions, the channel price should be cheaper. Therefore, users need to judge the price of the channel based on the load and the transmission conditions themselves. We use the function f here to express this relationship. Here, LID is the traffic load of DI, and LJU is the traffic load on unlicensed channel UJ. SC here is a feedback signal of collision. If DI collides with other D2D-U links or Wi-Fi users on the channel, SC is activated. So, as analyzed before, function f should decrease monotonically with respect to LID, and function f should increase monotonically with respect to LJU. And also, it should decrease with respect to Hij and should increase with the activation of SC. In order to quantify the fairness among D2D-U users, a new definition is proposed here. We introduce expected transmission time ETT as the ratio of a D2D-U link's traffic load to its achievable data rates. The fairness among D2D-U users can be then described as the equal ETT values of all users, as shown in this formula. As function f here is difficult to design directly based on mathematical or physical models, so the online trained neural networks are utilized to achieve adaptive adjustment of channel prices. You know, neural networks have the ability to fit nonlinear function according to the target. Here we use f hat here to represent the forward propagation of neural networks, and Cij hat represents the output as well as the price estimated by neural networks. Here phi is the weights and bias parameters of neural networks, and LID, LJU, Hij are normalized as the input of neural networks. Here Q is the loss function, and alpha is the learning rate, and phi is updated according to the backpropagation algorithm. The picture on the right shows the structure of the distributed network. Here each user trains a network separately and judges the prices of channels. MBS will provide part of the training information for D2D-U users. As networks are trained unsupervised, the loss function Q is the key to decide the performance of function f hat. Here, the loss function Q is formulated by two parts to train the neural networks in an online unsupervised way. Here Q1 affects the fairness among D2D-U users. If ETT value of DI is larger than half of users, which means that DI has used too many transmission resources, the prices for DI should be enhanced, and Q1 is equal to Q. When the opposite, and Q1 is equal to minus Q, else Q1 is equal to 0. Here Q2 affects the fairness of Wi-Fi users. If DI collides with other D2D-U links or Wi-Fi users, Q2 is set to V1, else Q2 is set to V2. Accordingly, the target of neural network output is denoted as here, as T. And Q can be calculated by L2 loss as here. It should be noted that Q1 and Q2 are all determined based on the feedback of SC and the feedback from the base station MBS. The entire algorithm is shown here. In each iteration, D2D-U users need to estimate the Wi-Fi traffic load first and judge the channel prices, and then solve the optimization problem and allocate the resources. Let's take a look at the simulation results. The simulation parameters are basically in Table 1 and Table 2. It's worth mentioning that in order to make the output more stable, we use a constant multiplied by sigmoid function to limit the output range to 0 to omega. The value of omega is decided by the total asset of D2D-U links C. And in the first simulation, there are two D2D-U links transmitting on two unlicensed channels. From the result, we can find that the outputs of prices converges quickly, and ETT values of D2D-U links D1 and D2 are basically equals. As for fairness of Wi-Fi system, after convergence, the traffic load of Wi-Fi system can be maintained at the basic guaranteed value, which is analyzed before. Actually, here D1 has a heavier transmission load than D2, and unlicensed channel U2 is less crowded than U1. As we expected, the trained result is that the price for D1 is lower and the price for U2 is lower. In the further simulation, the number of unlicensed channels and D2D-U links both have doubled. And centralized method to maximize throughput without considering the fairness among D2D-U users is provided for comparison. From the table, the ETT values of D2D-U links in our approach are same, and the centralized method obviously not fair enough. Right side is the power allocation for two methods. It can be seen that regardless of the high or low traffic load of the unlicensed band, the power allocation of the centralized method has not changed, and price-based model achieves adaptive adjustments to protect the performance of Wi-Fi users. In terms of total throughput performance, the result of the two methods here are close because the channel power gain and the power constraint are set to same. Maybe in a more practical situation, our method may cause a little loss. However, even if the centralized approach can achieve higher throughput, the resources may be allocated to users with little demands, which still leads to poor performance. Summarize our work again. A distributed power and spectrum allocation mechanism with adaptive price adjustment scheme is proposed for D2D-U system. A definition of Wi-Fi traffic load and ETT are proposed to ensure fair transmission of Wi-Fi users and also D2D-U users. An unsupervised online learning structure is employed on each D2D-U link to estimate the prices of all perceived unlicensed channels. A centralized optimal solution is presented for comparison, and the performance and fairness of this scheme have been well analyzed. I think this work is a simple exploration in this field to combine communication resource allocation with machine learning. There must be many improvements to continue study and try. For example, more complex communication environment modeling, such as unsaturated Wi-Fi transmission, and more comprehensive input parameters should be considered. Also, more powerful networks can be deployed through parameter sharing between D2D-U users. In order to achieve rapid convergence and ensure real-time performance, a very simple network structure is used in our article. However, parameter sharing may allow us to apply more powerful networks, and the parameters of the network can be updated in the form of such as federated learning at MBS. Maybe I think RNN-based models are also worth considering because the historical status information has a certain confidence, which can make the output maybe more stable and accurate. We have achieved the last part, and it's a sharing of our entire work. Sincerely thank you all for listening. If you have any question, you can ask me here or email me at zhouzhiqun@dgu.edu.cn. Thank you again.
Dear teachers and students, my name is Gou Junxiang and I am from Hebei University of Technology. The title of my talk is Graph-based terminal ranking for Sparsification of interference coordination parameters in ultra-dense networks. My speech will be conducted from the following 5 aspects. The first part is background. We will briefly introduce the research significance and the research status. The picture on the left shows a complex heterogeneous network, including device-to-device communication, millimeter wave communication, duplex communication, and so on. The picture on the right shows a comparison of key capabilities. Compared with the 5th generation, the 6th generation will provide higher speed, greater capacity, and ultra-low delay. Due to the limited spectrum resources, intercell interference becomes the main factor that restricts the system performance. Interference coordination has always been a difficult problem in the field of wireless communication. As far as research status, there are many traditional interference coordination schemes. Besides, other researchers have tried to use deep reinforcement learning to solve some interference coordination problems. In order to meet the communication requirements of each terminal and improve the system performance, the interference coordination scheme needs to consider multiple characteristic parameters of terminal. The huge data will greatly increase the computational time of resource management. Therefore, we should compress our data by sparsification of parameter to reduce the size of solution space before interference coordination. The second part is model. We will briefly introduce the system model and objective. We consider a communication serial, multiple cells, and each terminal has m characteristic parameters. We can represent this as a matrix CP, where the capital N represents the total number of terminals in a cell. We can express the optimization goal as max FCP. Since the original N is very large, the original optimization time will be too long. Therefore, we obtain a new matrix CPS for the decreased wavelet transform of CP for each row. Of course, the optimization objective has the same form and expressed as minus FCPS. Because of the characteristics of wavelet transform, the relationship between NS and N is exponential, so the computational time of solution must be greatly reduced. On the other hand, in order to ensure that the performance of the optimal solution is not significantly different, CPS can roughly reflect the variation characteristics of CP. We need to rank CP. This paper adopts graph theory to model the problem. Terminals are the vertices of the graph. Each represents the degree of difference between any two terminals, and the weight of each Vj is denoted as Wij, which is the Euclidean distance calculated according to the parameter values between terminals. Then the graph theory knowledge is used to find the ranking strategy of terminals. The ranking result, the terminals should satisfy the requirements that the distance between any two adjacent terminals should be as small as possible. So the terminal ranking problem is transformed into the problem of finding the minimum Hamiltonian path. It is expressed as the following formula. The third part is scheme. we will introduce the proposed terminal ranking scheme based on graph and its application. The minimum Hamiltonian path is an NP-hard problem, which cannot be solved in polynomial time. We can get a minimum Hamiltonian cycle and then remove an edge to get a Hamiltonian path, usually removing the edge with the largest weight. There are two common algorithms to solve this problem. One is search algorithm, such as simulated annealing algorithm, genetic algorithm. The other is approximation algorithm, such as nearest neighbor algorithm, double spanning tree algorithm, and classified algorithm. The number or formula behind the algorithm represents their approximate ratio upper limit. It is used to ensure the ratio of the cost of approximation algorithm to optimal cost. Among them, the search algorithms take too long time, which violates our original intention of reducing the time of interference coordination scheme. Therefore, we prefer to use approximation algorithms to get a better solution of the above problem in a short time. The graph on the left shows the solution process of nearest neighbor algorithm. Set A as the starting point. A Hamiltonian cycle ABDECA with weight of 37 can be attained. In the picture, bound length represents the selected edges and the arrows represent the selection order of each vertex. In the process, the edge with the lowest current weight is selected each time to get the next vertex, which will make the selection of the last two edges unique. If one of the edges has a larger weight, the approximate solution will be poor, such as edge DE and EC. The picture in the middle is the solution process of double spanning tree algorithm. A minimum spanning tree is first obtained, as shown in the sequence, and then double its edges to obtain an owner diagram, as shown in picture. Then an owner cycle starting from point A is AEAD, ABCBA, and the final Hamiltonian cycle is AED, BCA with the weight of 35. Because there are many ordinary cycles, the Hamiltonian cycles obtained are not unique. However, some distant points will not appear continuously in any closed trace, such as EC. The picture on the right is the solution process of classified algorithm. A minimum spanning tree is first obtained, as shown in the bound length. Find out the odd degree vertices, as shown circled vertices. Find its minimum with perfect matching as AECD. Add the matching edges to get an inner diagram. An inner cycle from point A is AEAD-CBA, and finally Hamiltonian cycle is AED-CBA with the weight of 32.5. Similar to double spanning tree algorithm, classified algorithm can also avoid selecting the edge with large weight. For considering the characteristics of terminal mobility, power, business flow, and so on, the change period is usually much larger than the millisecond level. Therefore, we design a two-cycle resource management application framework. When a larger cycle update is reached, the graph-based terminal ranking method will be used to ranking all the terminals. Then, during each resource management cycle, terminals requiring coordinated interference are identified according to business requirements, and the order of these terminals is determined based on the ranking results of the non-cycle. Finally, the remaining interference coordination steps are performed sequentially. The update cycle of terminal parameters is much larger than a resource management cycle, so that several or dozens of resource management processes can be effectively carried out within a larger cycle. The fourth part is discussions. We will introduce simulations of all performance indicators of different schemes. This page shows a simulation comparison of Zhenyu index of different schemes. The corresponding performance of 3 Hamiltonian path algorithms for terminal ranking is better than that of low ranking method, which indicates the sparsity of parameter matrix is greatly improved after ranking. It can also be seen that the performance of the 3 algorithms for solving Hamiltonian paths differs little. In comparison, the Zhenyu index of the nearest neighbor algorithm is slightly better. This page shows a simulation comparison of reconstruction errors of different schemes. Similarly, the corresponding performance of 3 Hamiltonian path algorithms for terminal ranking is better than that of low ranking method, and the reconstruction error of the Christopher's algorithm is slightly worse. In addition, when the number of decomposition layers is too large, the reconstruction error of the nearest neighbor algorithm will steadily increase. This page shows a simulation comparison of capacity per resource block of different schemes. It can be seen that the capacity per resource block is not significantly affected by the removal of wavelet coefficients in interference coordination, which is better than directly using wavelet decomposition without ranking to reduce the problem size. And it is found that the sparsity of considering one parameter more makes the capacity per resource block of the network slightly increase, and the difference of the capacity per resource block of various algorithms slightly decrease. This page shows a simulation comparison of Zhang's fairness index of different schemes. It can be seen that the fairness of terminals is greatly improved due to the use of wavelet transform. However, the ranking scheme will make the fairness somewhat lower, which is lower than the method of using wavelet transform directly without ranking. At the same time, it is found that the sparsity of considering one parameter more will lead to a slightly decrease in the fairness of terminals, and the difference of the fairness of each algorithm will also be slightly reduced. This page shows a simulation comparison of time cost of different schemes. The picture on the left shows time cost of interference coordination, As can be seen, the use of wavelet transform can significantly reduce the size of the problem, so that the time cost of interference cancellation is only 1% of magnitude of the traditional scheme. The picture on the right shows time cost of terminal racking. As can be seen, nearest neighbor algorithm has the minimum time cost, because it only ranks according to the relative size between sequence values. When the number of terminals is small, the classified algorithm is more time-consuming than the double-spanning tree algorithm, because the step of minimal with perfect matching of the order-degree vertices introduces a lot of time. But when the number of terminals is increased, the classified algorithm is less time-consuming than the double-spanning tree algorithm. This is because it may take less time to find an unreal cycle. The last part is conclusion. We will briefly summarize the content of this paper. First, graph-based terminal ranking method for sparsification was proposed. Second, towards the ranking of multiple parameters sequences into the ranking problem of a terminal sequence. Third, use the approximation algorithm to solve the NP-hard problem of terminal ranking. The last one, design and two-cycle application framework for terminal ranking and interference correlation. This is the end of my speech. Thank you for listening.
Hello everyone, this is Xiujun Wang from Iowa University of Technology. My report title is An Efficient Protocol for Tech Information Sampling in RFID Systems. So the outline of my report is that the first part we will talk about problem background, then we will discuss its definition, and then we will discuss the load bound analysis, and in the fourth part we will show the efficient solution for this problem. In the fifth part, we will show the experimental results for this problem, and then we come to the conclusion. So the background of this problem is quite interesting. Recently, radio frequency identification technology has been widely applied in tracking moving objects, managing supply chains, and controlling warehouse inventory. When an RFID tag is equipped on, every physical object can become part of a network and then are managed and monitored in an efficient way. So conceptually, an RFID system in this application consists of the following three components. The first component is RFID tags, each of which carries a unique 96 bits or 128 bits stored in its chips, and are attached to different physical objects and serve as unique identifier of this object. A tag also carries the tag information, which can either be the attribute of data of the tag object or the sensor data. The second part is the RFID readers, each of which is deployed to a location to monitor the behavior and connect the tags for the tags within its range. The third part is backend server, which connects each readers in an RFID system and offers them with the needed information and computation support. We show an RFID system in this picture. In this picture, the inventory computer serves as the backend server. Then we see the RFID reader, which is equipped with an antenna and used to interrogate the RFID tags within its range. The practical significance of the tag information sampling problem is quite obvious. Because it is a problem that requires to randomly pick k tags from a large population S to construct a subset T, and then inform each of the tags in T of a unique order from 1 to k. This function has a wide range of application in many tag management problems, such as monitoring and gathering tags information. The point is that when the user needs to analyze the data and characteristic of a large population S, it's time-consuming and sometimes unnecessary to connect the tag information from every tag in S. In contrast, the tag information from a random tag and a small subset T is good enough. So we see examples. So in this example, we take WSP tags, which is a kind of tag that can feed back its ID as well as real-time sensor data related to the state of the tag object or the surrounding environmental conditions. In such scenario, where we need to periodically connect sensor data from the large tag population, it is common that we randomly choose a small number of tags at a time and connect their sensor data. Due to the redundancy in environmental data, it is unnecessary to ask every tag to report their data. So the tag information sampling plays an important role in IoT networks where massive data captured by various sensor-augmented RFID tags usually contains a large amount of redundancy. So even though there are some existing problems that seem to solve these problems, but there are some limitations. For example, there are some protocols that can targeting at how to connect information of either the whole population or a specific tag subset B. This limitation incurs a high communication cost when we apply this protocol to solving the study problem. There are also some research work for connecting specific information from a tag population which has been pre-divided into multiple groups. And these protocols are also limited by this requirement because it needs to pre-divide a large text population into multiple groups, and this requirement is not true in the problem setting of over problems. Then we will give the problem definition. So we consider an RFID system that includes only one reader and a population S of n tags, and all the tags in S are within the interrogating range of reader R, and each tag carries an ID which is denoted by TID, and also and also some data related to this tag and denoted by T-info, which is needed by the reader. Then formally we define this problem. In an RFID system, let K be the predetermined size of the sample subset. The tag sampling problem requires to design a protocol between the reader R and tags such as the following two requirements are true. The first requirement is that a random subset T of K distinct tags is selected from the whole population S, and every possible subset of K distinct tags share the same possibility of being chosen as T. And each tag in T is informed with a unique order ranging from 1 to K. So let's take an example to have a better understanding of this problem. For example, we consider an RFID system consider tag population of only 3 tags, and we set the sample size T to be 2. And then the tag information sampling problem design a protocol that picks 2 tags randomly from S and informs them with the unique orders, or namely the following. So the first thing we say that the probability T1 and T2 are selected and informed with unique order happens with a probability of 1 over 3. And T1 and T3 are selected and informed with unique order happens with a probability of 1 over 3. And lastly, T2 and T3 are selected and informed with unique orders happens with a probability of 1 over 3. So let's see a picture to have a whole and have a better overall understanding. So in this example, we show a tag population of 7 tags, and there is only one reader, and then which is connected to the backend server. Please notice that the backend server has already connected the IDs of these 7 tags, and then the reader need to select, say, 2 tags, randomly select 2 tags from these 7 tags, or randomly select 3 tags from this tag population. So then we will talk about the lower bound. So we need some notation to explore the lower bound. First of all, we use TID to represent a time frame for the reader to broadcast a 96-bit array to all tags within the range. And we use S to represent a population of n tags, and K represents the size of the wanted random subset, and U represents the universe of all the possible tag IDs. So the basic idea of the proof is that we first assume that there is a protocol that actually solves the problem, and then we transform the protocol P into an encoding method that can accurately represent tag population S. Certainly, the low bound can be derived from the minimal number of bits required by this encoding method. So more formally, we have this symbol, which says that if a protocol solves the study problem, it must need to transmit 1.44 times k bits to all tags, and consequently, the communication time of P can be no less than this number. So the detail of the proof can be found in our paper. So according to this low bound, we shed some light for the efficient practical solution. According to Summer 2, solving the problem, we need a communication cost of 1.44 times k. But a naive solution that first lets the reader determine the k random text from S and then inform the k selected text by broadcasting their IDs costs us 96 times k bits. Since that there is a large gap between 1.kk and k 96 times k, we see that a large potential of efficient practical solution. So the basic idea of the protocol, we divide the job into 2 phases. The first phase is to isolate k random tags from S, and the second phase, denoted by PS2, is to inform each of the k tags a unique number from 1 to k. next, we define the three status of a tag. So we say a tag is in unselected tag if it does not know whether it is selected or not, which means that all tags are initialized in this state. And we say a tag is in acknowledged state if it means that it has determined that it is selected and has already been informed with a unique order number I. And if a tag is in inactive text, it means that it has determined that it does not need to report anything to reader, and it should keep silent in the subsequent process that connects tag informations. So the design of the first phase is quite simple. It just used one communication round. In this round, reader R first send a random number R to all the tags, and upon receiving this random state, each tag T computes a random number HT, and if the value HT is less than T, this less than K, tag T shall remain in unselected state. Otherwise, T will enter the inactive state. So we first prove the correctness of this of the first stage. So given a tag population S of n tags after PS is finished, the probability that the k distinct tags are choosing to remain in unselected state is equal to k factorial divided by n following factorial. So the basic idea of the proof is that since that the reader has a foreknowledge of all the IDs and it can predict the hash values of each text, and then it can choose a proper random seed to guarantee that the first requirement of the study problem is achieved. Then we analyze the communication cost. The communication cost is log n, just like the sum of 4 stated. The proof is that because according to reference 4, we know that log n bits are sufficient to describe a hash function, and then it is sufficient to describe a random number. Then we will talk about the design of the second stage. The second stage is just the task is to inform the k tags remaining in the unselected tag with unique integers from 1 to k. So with this task is fulfilled, the whole problem is solved. So it contains 6 steps. In this slide, we show the first 3. So let B represent the set of the k tags that is in unselected state. So first of all, we test if B is empty set, right? So which means that the problem is solved. Read R does not do anything. Otherwise, if it is not an empty set, read R starts a new communication round by broadcasting a request with 2 random numbers. The first with 2 numbers. The first number is B, which is the size of the set B, and the second is R, which is random number. After receiving B and R, each tag in the unselected state computes a random number FT. And since R knows the IDs of all the tags in B, it can predict the value of FT for every tag and construct a FT like this. We will talk about the detail of FT in a following running example. And then read R broadcast bit array F off, and after receiving F, so then tag T will check the position FT, will check the FT's bit in the array F. So if it is 1, it will enter the acknowledged state. Otherwise, it will still remain in unselected state. So we take an example to understand the second phrase. So say that initially B contains 5 tags, which is T1, T2, T3, T4, and T5. Say that T1 is hashed to the second bit F2, and T2 is hashed to the first bit F1, and T3 is hashed to the second bit. So in this case, we will set F2 to 0 because there are 2 distinct tags hashed to this hashed to F2. And after the by the first round, we see that T2, T4, and T5 enter the acknowledged state because their corresponding bit is 1. And the other 2 tags, which are T2 and T3, remain in unselected state. And then T1 and T3 will enter the acknowledged state in the second round, just similarly as the first round. So then we will analyze the performance of theoretical performance of PS2. So it is first easy to observe that after the second phase, each tag in B obtain a unique order from 1 to k. And then we will talk about the communication cost of the second phase. During PS2, reader needs to send about this number of bits to all tags. So the basic idea is that we will first find the fact that in each round, a fixed proportion of tags in B enter the acknowledged state. So by using this insight, we can get the thermal easily. The detail can be seen in our paper. So then in summary, we will talk about the total communication of the proposed protocol. The communication of PS is about 2 times of the low bound. So this thermal can be proved easily based on the result of thermal 2, 3, and 7. Then we discuss the experiment. So in the experiment, we adopt the state of the standard EPC Global C1G2 standard, which has been used widely to test the protocol performance in RFID systems. We choose two state-of-the-art protocols, which are minimal perfect hashing-based information connection and the tag ordering polling protocol. And we used 4 different scenarios to test the performance of these 3 protocols. And each scenario is just characterized by a unique relationship between the k, which is the number of tags in a sample subset T, and n, which is the number of tags in tag population S. So to be more specific, in scenario 1, we set n to be fixed to 10 to the power 5, but vary k from 10 to the power 2 to 5 times 10 to the power 2. In scenario 2, we fixed k to the 10 to the power 2, but vary n from 10 to the power 4 to 10 to the power 5. In scenario 3, we change both n and k simultaneously, but we keep the ratio to be fixed at 10 to the power of minus 1. In scenario 4, we take the similar setting as scenario 3, but we change the ratio between k and n to be 2 times 10 to the power of minus 1. And then we show the result of scenario 1. We can observe that the blue line, which is over protocol, is much less than the other 2 protocol, and actually it is quite close to the low bound, which is shown in the black line. And in scenario 2 and scenario 3 and scenario 4, we have the similar observation. So by this experimental results, we can observe from the experiment that the communication time of PS, which is over protocol, is smallest among the 3 protocols. Indeed, it stays close to the low bound. And taking scenario 1, for example, when k equals 10 to the power 3 and n equals 10 to the power 5, the communication time of over protocol is only 0.12 seconds, where the communication cost of top and PIC is much larger than overs. So in summary, we observe that the over protocol has a communication time that is only 10% to 20% of the other protocols. And the superiority of a protocol comes from 2 facts. The first, because over protocol allows the tag T in S to randomly decide to join in the random subset T or not locally, whereas the other protocol lets the reader first to globally determine the subset K. Secondly, all protocols smartly transmit a small number of bits by focusing on the K tags out randomly from the population S, while the other protocol must use a much more number of bits to take a good care of every tag in S, such that the 2 requirements of the study problem is achieved. So in conclusion, in this report, we studied the problem of tag information sampling problem in RFID systems. We first obtained a low bound of the communication cost and proposed an efficient protocol for this problem. The proposed protocol PS has a communication cost that is not only much less than that of the state-of-the-art protocols, but proven to be, within a factor of 2 of the low bound. So lastly, through extensive simulation results, we verify the theoretical result. So this is a reference of our report. Thank you very much for your listening and watching.
Hello everyone, I am one of the authors of this work, Zhou from Zhejiang University, Hangzhou, China, and I'm honored to get the opportunity to introduce our work, Spectra-efficient spacetime coding, to everyone here. I will first introduce the background of our work, the shortcomings of traditional methods, as well as the problem we want to solve. Then, I will briefly talk about the contribution of our work. Next, the classic Alamuti scheme will be introduced. The data transfer process of a 2-to-n MIMO systems and its spectral efficiency loss are analyzed. Aiming at the loss of the classic Alamuti scheme, our new STBC scheme will be proposed. Its improvements, computational complexity, and BER performance will be analyzed in detail. Simulation results will be then analyzed, including Monte Carlo simulation and BER performance comparison with the classic STBC scheme will also be arranged to prove the effectiveness of our scheme. The last part is the conclusion of our work. So let's first talk about the background of this paper. Multiple input, multiple output, known as MIMO, must be familiar to everyone. And the massive MIMO technique has already become one of the key technologies for 5G communications. It uses multipass effect to improve communication quality, and also can improve the spectral efficiency tremendously by introducing the spatial freedom. By using MIMO technique, both diversity and multiplex gain can be achieved to improve the transmit data rate and reliability. To achieve this diversity and multiplex gain in a practical MIMO system, Alamuti space-time block code, known as STBC, has been proposed. However, most works related to STBC sacrifice either the diversity gain or the complexity of the detector at the receiver to achieve more spectral efficiency. Then, to solve the problem, a new STBC scheme is proposed in this paper to improve the system's spectral efficiency while retaining the simple linear maximum likelihood detector, and also the diversity gain of the classic Alamuti scheme. The basic idea of the new scheme is to transmit more information by exploiting the sequence of transmitted symbols in time domain. The details will be placed in the later part. Here is a brief summary of the contribution of this article. A new space-time coding scheme is proposed to improve the system spectral efficiency while retaining the simple linear maximum likelihood detector and also the diversity gain of the classic Alamuti scheme. Both analysis and Monte Carlo simulation results are utilized to verify the efficiency of the proposed scheme. We also compare our coding approach with the classic STBC scheme, and the results show that the BER performance is close to the classic STBC scheme. Let's first look at a MIMO system with the classic Alamuti scheme. In the system, we assume that there are two transmit antennas and NR antennas deployed at the receiver. The source bits are first divided into two streams. Each binary stream then goes through a modulator to map bits into symbols, x1 and x2. The received signals, YC, is given by here Y1C at time slot 1 and Y2C at time slot 2. Here symbols x1 and x2 are transmitted by antenna 1 and antenna 2 at time slot 1. And minus x2 star and x1 star are sent via two antennas at consecutive time slot. H1 and H2 are channel gain vectors, and N1 and N2 are noise vectors. The average SNR at each received antenna is shown here. So in this paper, we assume that the channels are quasi-static frequency flat Rayleigh high fading channels. Therefore, H1 and H2 do not change in one transmission interval, and the items in H1 and H2 are the complex Gaussian variables. When the receiver has the perfect channel state information CSI, it manipulates the received signals to yield. Define H like this, and then the receiver computes the following metric to have Z. Due to the orthogonal structure of the Mulit code, the equalized symbols are calculated as x1 hat and x2 hat here. Then the receiver can recover the transmitted symbols by demodulating x1 hat and x2 hat. So here symbols x1 and x2 are transmitted in the first time slot, and redundancy related to x1 and x2 are transmitted in the second time slot to exploit the diversity gain in spatial domain. So since the same information is transmitted in two consecutive time slots, spectral efficiency is sacrificed. Therefore, to improve the spectral efficiency, another Mulit coding pattern is designed in this paper by switching the transmitted symbols in two consecutive time slots, so that one more bit can be carried. In the proposed scheme, the received signals yn is given by here y1n at time slot 1 and y2n at time slot 2. Here n means new. It can be observed that only difference between the new Mulit coding pattern, we can say NAP, and the classic Mulit coding pattern CAP is that minus x star 2 and x star 1 are transmitted in the first time slot, and x1 and x2 are transmitted in the second time slot. Therefore, the orthogonal structure is still preserved in new scheme, and the simple ML detector can be used to recover the transmitted symbol at the receiver. So in order to carry one more bit, transmitter can select either the classic CAP or the new NAP scheme in each transmission interval, based on the value of a variable b. When b is equal to 0, the classic CAP-based method is selected. Otherwise, NAP scheme is chosen as the transmitter. The new transmission scheme is demonstrated in Figure 1 here. And the detection scheme at the receiver is concluded in algorithm 1. From the algorithm 1, we can find that we first calculate and compare YCAP and YNAP based on CAP and NAP respectively. And then we could determine the final output based on the result of the comparison. The new scheme also has the advantages on low detection complexity. At the transmitter, it only needs to swap the ST code symbols of different slots, which is easy to be implemented in practice. Comparing to the STBC SM-based method, when M-array modulation is used in the system, at the receiver, the computational complexity of our approach is O4M, and it's OCM squared in STBC SM-based method. Here, C is the number of possible channel combinations. Of course, the proposed scheme can also be applied to the system with more than 2 transmitter channels. As for BER performance of the proposed scheme, an asymptotic BER performance bond for the proposed scheme is analyzed when MPSK or MQAM modulation are applied. Since it is hard to derive a closed form expression for the joint detection, we assume that the index and symbol estimation process are independent to derive a low bound on BER of the proposed scheme. Here, let Pi be the BER of index estimation given that the symbols are perfectly detected, and PS here be the BER of symbol estimation given that the symbols are perfectly detected. Then the BER of the system is lower bounded by PB here. It is noteworthy that algorithm 1 detects the index bit B and transmitted symbols jointly. As a result, the assumption of independent estimation process is not realistic and cannot reach an accurate BER performance. But with this assumption, we can derive a closed form BER lower bound for the proposed scheme as presented of PB. Under the assumption that the index bit can be recovered correctly, the detection for symbols in our scheme is equal to the detection process for the Alamuti scheme. Therefore, the SER over a Rayleigh high fading channel is given by PSK here. On the other hand, when M array QAM is used, the SER is expressed as PSQAM here. And finally, the BER PS can be then derived from the approximate relationship as here. As for simulation results, the Monte Carlo simulation results are presented to demonstrate the performance of the proposed scheme. Besides, the 16 QAM and 16 PSK-based STBC methods are used as references to validate that the BER performance of the proposed scheme is close to that of the conventional STBC scheme. Assuming that the receiver has the accurate quasi-static frequency flat Rayleigh high fading channel information, and the gray-coded MQAM and MPSK constellation points are used in the system. Let's first look at Monte Carlo results. Figure 2 demonstrates the BER performance of the proposed scheme by the Monte Carlo simulation when 16 AQM is used. It is evident that the formulated BER is lower bound of the simulation results, which validates our analysis before. In Figure 3 and 4, we compare the BER performance of the proposed scheme with the classic STBC scheme when 16 PSK and 16 QAM are used. We can observe that both schemes have the same slope, which means that our scheme can exploit the same diversity order as the classic STBC scheme. Moreover, the BER performance of the new scheme is very close to that of the classic STBC. Therefore, without sacrificing the BER performance, the new scheme can improve the system spectrum efficiency by 25% when 16 QAM or 16 PSK is used in the system. Then briefly summarize our work. A new STBC scheme is proposed to improve the transmission data rate while retaining the diversity gain of classic STBC scheme. Additional information bits are carried by using different STBC coding patterns in time domain. The efficiency of the scheme has been verified by both analysis and Monte Carlo simulation results. Besides, the BER performance is verified of the proposed scheme, and it is close to the classic STBC scheme, and the simple detection scheme at receiver is inherited from the classic STBC scheme. Here we have achieved the last part, and it is the sharing of our entire work. Sincerely thank you all for listening. If you have any questions, you can ask me here or email me at inray@ducc.edu.cn. Thank you again.
Hello everyone, I'm Zhang from Zhengzhou University, and I will give a presentation about the 5G health networks and related service from theory to reality. Here is the outline of my presentation. First, as we know that the current technology advancement and the investment are revenue driven. In such a scenario, if there is a lot of people, then more potential revenues, and we will give more investment, and the technology advancement is for such a to deliver the service to such a area, and in an area that is with less people, then less potential revenues and less investment and technologies. What is the result? For example, this is in our Henan province, the capital city, Zhengzhou. And this is the remote villages in our province. As we know that since most of the young middle-aged people move to big cities, the elderly, ill, and disabled people are left behind in these remote villages. And actually, because of the revenue-driven investment and the technology advancement, the digital gap between the big cities and remote villages are getting even larger. And the people left behind in the remote villages are the ill and disabled, and also the children. They are the ones who indeed need high quality medical services, but in the remote villages, the medical infrastructure is inferior and lack of the high quality medical services. What shall we do? The ICT assistant in-house, actually, it is not a new topic. It has been proposed by the ITU since 1990. But the current ICT assistant in-house technology has some weakness, especially because the current wireless connections and the current communication technology can only connect about, for instance, in one cellular area, we can only provide service to about 20 users. And the current wireless communication transmission speed is about several megabit per second to 1 gigabit per second. I mean the peak rate. And the experienced rate is about several megabit per second to 10 or 20 megabit per second. The transmission speed is really slow and cannot transmit the high quality, high definitive medical videos. And the current wireless technology, the latency and performance is here, and it cannot deliver the reliable communications and or connections. In such a case, 5G is really good solution. Here's the KPI that summarized by the EU H2020 project 5G Heart. And based on that, we propose the 5G in-house service and related technology that is listed in this figure. As we can see that we can connect all of the remote hospitals, and for the in-home health with the connect body area sensors to the mega hospitals to share the high quality medical services of the mega hospital. In such a scenario, the related 5G technology can be listed as below, mostly from the physical layer such as maximum millimeter wave terahertz NOMA, and from the upper layer like the Ethernet, HARQ, edge computing network slicing. As we know that 5G has claimed the three typical application scenarios, that is the massive machine type communications, enhanced mobile broadband, and also the ultra reliable and low latency communications. All of these feed the in-house system applications perfectly. And as we just talked, the related 5G air interference technologies can be listed from the physical layer and also the optic and the cause layer. Since the physical layer has been investigated a lot, so we just ignore them. And let us check the network slicing technology and mobile edge computing technologies. In such a scenario, we employ the GMTN Flex E technology to divide the physical infrastructure into different hard slices, and each hard slice can support about 1 gigabit per second transmission speed and can be further divided into several megabit per second sub-slices. And these sub-slices can be dedicated to different applications. And we can also create the private channel and shared QoS guaranteed channel with our GMTN Flex E technology. In a private channel, all of the physical infrastructures are dedicated to this channel, to these applications, but in a shared QoS guaranteed channel, it is created some dedicated shared application channel with Flex E interference from the common physical infrastructure. And on the other hand, we also use the mobile edge computing technologies. Here is our MEC architecture, and we also use the GMTN FlexE technology to support different mobile edge computing services. In such a scenario, we can use the intelligent application sensing and edge intelligence to learn from the existing network performance and for the next usage. And in such a scenario, we also use the edge cloud signature for the global intelligence and local decision. Here is our field trial result of our 5G health network, and we use the non-standalone and standalone deployment of our base stations, and we use NC to stand for the congestion network conditions. And here is our record. As we can see that if in a standalone scenario, the downlink speed can be guaranteed, but with the non-standalone, especially when the congestion happens, the speed cannot be guaranteed, such as here and here and here. And our latency performance is around 10 milliseconds, and the uplink speed is about 18 to 90 megabit per second with our 5G technologies. And after that, we will demonstrate two typical applications for the remote health and the COVID-19 containment. Here is our 5G health system for the remote area scenario. We connect the remote village hospitals and clinics to our mega hospitals, to our specialty hospitals in the mega cities with the 5G networks. And in Henan province, we connect the 18 perfect city and 108 country clinic to our Zhengzhou capital city hospitals. That is the first affiliate hospital of Zhengzhou University. For instance, we demonstrate the remote e-health system with our 5G networks from the Huaidian village Guangshan Xinyang, and this clinic is connected to the FEH-ZZU. In such a case, the patient from Huaidian village Guangshan Xinyang can share the high quality medical services from the FEH-ZZU, and the expert can remotely diagnose and give suggestions according to his ultrasound B record. And from this scenario, we test that the uplink transmission speed is about 100 megabit per second, and our network latency performance is 7.6 milliseconds. And we can also use the 5G health system for first aid and also for the emergency rescue with our in-vehicle with our 5G enabled ambulance vehicles. In such a case, we can deliver the in-vehicle remote diagnosis and treatment, and we can also share the medical records and the vital signs of our patient from all of these devices in the vehicle. Or even in some emergency case, we can deliver the remote in-vehicle surgery. But due to risk, we didn't demonstrate the remote surgery in our scenario. That is mainly because of the URLC performance of our current 5G networks cannot be achieved. We then pressed two white papers about the 5G e-health system, that is the 5G intelligent health white paper and also the 5G intelligent medical network and the elastic network slicing technology white paper. And you can download it all the two PDF online. Then during the COVID-19, our 5G health system also have demonstrated its abilities. And first, this is our ZZU medical team in Hubei. And from the first day, Wuhan was closed. In the following 1 week, we connected the 147 prefecture level hospitals from our 108 prefectures to the mega hospitals in Zhengzhou city. That is the first affiliate hospital of Zhengzhou University. In such a case, the expert, the medical doctor can remotely check the patient condition. Then the physical contact is reduced, and the one medical doctor can remotely check multiple patients from different places. And with all of these connected devices, we can deliver the 24 hours monitoring and timely response to our patients in an isolated ward room if needed. And we can also deliver the online training and conference by our 5G health systems. Here is a record from one medical expert. There's also some challenging issues and future studies. First, from the technical perspective, especially for the URLC currently, the claimed URLC performance cannot be achieved by the current wireless technologies. And on the other hand, since most of the patients' vital signs and private and personal information are connected by are monitored by the devices and then transmitted by the 5G network. So how to ensure the transmission security and how to protect their private information is a challenging issue for 5G health applications. And on the other hand, the augmented reality and artificial intelligence applications, especially for the remote surgery. there is still a lot of work to do. On the other hand, from the society and the government perspective, the telemedical service is needed in the future studies, especially in the developing countries. And on the other hand, we need the word standardization and legitimation for the 5G health system applications from countries to countries, from different nations to nations. Thank you.
The title of our report is A Video Surveillance Network for Airport Ground Moving Targets. I'm Zhang. We are from the University of Electronic Science and Technology of China. The background of our work is as follows. With the continuous growth of civil aviation traffic, the airport ground is getting busier and crowded. The airport must be more intelligent to face operation and capacity challenges. The airport ground is where the plane takes off, lands, and taxis. The airport ground is a semi-military area, and the airport ground monitoring is very important for civil aviation safety. The motivation of our work is as follows. There are already some traditional surveillance methods for airport ground, such as the common secondary radar and automatic dependent surveillance broadcast (ADSB). Compared with these methods, the video-based intelligent surveillance is more promising because it contains rich information. Since the airport ground is very broad, it needs a network or multiple cameras to cover the whole monitoring area. We present a video surveillance network for airport ground moving targets. The proposed airport ground moving surveillance network is shown on this figure. Multiple cameras, including both fixed cameras and PDZ cameras, are installed around the airport ground. Captured videos in the form of H.264 are transmitted to the control center with a dedicated high-speed optic fiber network. In the control center, video data is processed and displayed on a large screen. Since the airport ground is very broad and the field of view of a single camera is limited, it is necessary to splice the videos based on the camera's geometric relationship. The spliced video is shown on the next page. Based on the spliced video, various intelligent applications can be developed for airport ground surveillance. The splicing results based on the 4-channel videos are shown on this page. The upper image demonstrates the splicing result during the day, while the lower image the splicing result during the night.
Various video-based intelligent applications can be developed for airport ground surveillance based on the video after splicing or video without splicing. Moving object detection is the basis of most video surveillance applications, especially for high-precision applications. Therefore, a larger main work of this paper is to propose a new moving object detection algorithm. The task of moving object detection is to segment the moving targets from the background as shown in the figure on this page. However, this figure also indicates that moving object detection in airport ground is very challenging, where many foreground pixels are misdetected due to the camouflage problem between foreground and background. The camouflage refers to the case that when the foreground and the background are similarly colored, the classification will tend to the majority class, the background. For this challenging problem, in this paper, a moving object detection algorithm is specially designed for airport ground surveillance by the use of the prior knowledge of the airport ground. The principle of the proposed moving object detection method is shown on this page and the next page. Firstly, we can see that the airport ground in figure A has a gray-white color distribution. In fact, all airports around the world are like this. Next, we compute the gray histogram of figure A from the AGVS dataset, which shows two significant peaks in figure B. The AGVS benchmark is any airport ground surveillance database for moving object detection. Since the airport ground is gray-white, we can infer that the two peaks in figure B correspond to the gray area and the white area of the airport ground, respectively. Next, we use a bimode Gaussian distribution to fit the gray histogram in figure B, as shown in figure 3. The bimode function not only shows the gray distribution of the airport ground pixels, but also reflects the occurrence probability of camouflage. Since the misdetection occurs between the aircraft and airport ground, if we can bias the classification to the foreground according to the occurrence probability of camouflage. The misdetection on page 6 may be compensated. Based on this idea, we propose a prime mode as shown in figure D. The prime mode is two weight functions based on the fitted distribution, where the variance is variable. The two weight functions are used to bias the classification to the foreground according to the occurrence probability of camouflage, as shown in equation 1. Equation 1 means that the greater the camouflage occurrence probability, the higher the probability of being classified as the minority class, the foreground. Therefore, the prime mode does achieve our goal. Next, the traditional bilayer mode as shown in equation 2 is used in conjunction with the prime mode for classification. We construct the bilayer mode in equation 2 non-parametrically, where a non-parametric mode is separately kept for the background and the foreground. Finally, moving object classification is achieved within the Bayesian classification framework, as shown in equation 3. The likelihood term in equation 3 is the product of the prime mode and the bilayer mode, as shown in equation 4. The smoothness term in equation 3 is based on the first order Markov random field. The final optimization is based on graph cut. There are many literatures on graph optimization and the smoothness term in Bayesian classification. Please refer to them for more details. The detection results of the proposed method is shown in figure 1. The first column in figure 1 are two typical frames from the HVS dataset. The second column are the ground truths. From the third column to the last column, the detection results of several classic moving object detection algorithms and the proposed method are displayed. We can see that the proposed method has the best detection results. The quantitative results of 11 algorithms on the whole HVS dataset are shown in figure 2. on this page. Three of the most commonly used performance metrics, RE, PR, and FM, are employed in Figure 2. The larger the performance index value, the better the detection performance. Figure 2 indicates that the proposed method does have the best detection performance on the HVS dataset. In addition, please note that the proposed method can only be used for airport ground video surveillance, since the prior knowledge of the airport ground is considered in our method. In other words, the algorithm is only for specific applications, but not a general algorithm. That's all. Thank you.
Hello everyone, my name is Chen Xuan. I'm from Chiba University in Japan. My presentation title is Characterizing Latency Performance in Private Blockchain Network. In the first part, I'd like to introduce the background and what we have done. The methodology is introduced in the second part, and the evaluation results are introduced in the third part. The final part is the conclusion. First, introduction. First, what is a blockchain? A blockchain is well known because of the cryptocurrency, such as Bitcoin. Blockchain is the underlying technology of Bitcoin, while the blockchain itself is a growing list of blocks. Each block contains two parts, block header and block body. The block header contains some parameters about the block itself, and the block body contains records or transactions happen in the blockchain network. Those blocks are associated with each other by the hash of the block and the hash of the previous block. In a blockchain network, every node holds a copy of all previous blocks, so the record or transactions inside of the blocks becomes immutable and transparent. Thus, the blockchain network doesn't rely on any centralized third party. Except the cryptocurrency, the blockchain technology can be used in many other places, including the Internet of Things. The current IoT system faces many challenges because of the centralized structure, such as one-point failure, scalability, and security. While the blockchain has the nature of decentralization, the combination of blockchain and IoT can solve some challenges. There are many blockchain networks, and we can generally divide them into two parts, which are public blockchain network and private blockchain network. A public blockchain network allows users to join and live without any restrictions. Well, you need to be permitted to join a private blockchain network. The public blockchain network is usually of large scale and is usually used in finance. A private blockchain network is usually of small scale and it allows us to create our own customer network. So the private blockchain is more suitable for IoT, especially in some small scale network such as smart home. A smart home is one of applications combining blockchain and IoT. Instead of using a centralized device to control all appliances, the blockchain-based smart home allows appliances to maintain a blockchain network. Shared information and activities will be recorded in the blocks. And for those blockchain-based applications, there are some frameworks to evaluate the performance, such as Blockbench. Those frameworks mainly evaluated throughput, latency, scalability, and security. They had very excellent explanations on throughput, scalability, and security, while there are some limitations when evaluating latency. First, the previous framework only considers the latency of transactions. They lack the latency of blocks. Second, the previous framework only considers the latency in one node. They lack the latency of transmission between different nodes. So we evaluated the latency. We characterize the latency in private blockchain network. First, considering the nodes interaction, we clarify the transmission process of transactions and block, which is the transaction lifecycle. Then we define two different types of latency based on the transaction lifecycle. They are transaction-oriented latency and block-oriented latency. Then we measure the defined latencies in a real deployment. The second part is the methodology. We choose to use Ethereum for our implementation because Ethereum is one of the most popular open source blockchain platforms. Ethereum uses proof of work algorithm to generate new blocks. The proof of work algorithm requires nodes to solve a mathematical problem, and the process of solving the problem and generating new blocks is the mining process. The biggest feature of Ethereum is that it supports smart contracts. Smart contracts are code stored in the blockchain. And if a transaction calls the functions in the smart contract, the smart contract will run automatically. Because not every IoT devices can do the mining work, so in Ethereum-based IoT network, a transaction needs 3 steps to become effective. First, a node A submits a transaction. The transaction needs to propagate to a mining node. Second, the mining node might block contain the transaction. Third, the block is transferred back to node A. When the block transferred to node A, the transaction comes into effect. We define from the transaction submission to the transaction comes into effect at the transaction lifecycle. In the transaction lifecycle, we define the first process of transaction propagation at the transaction-oriented latency. We define the third process of block propagation at the block-oriented latency. Then for the second process, the mining process, because the mining time is different in different private blockchain network, and also the transaction may arrive at the mining time in the middle of the mining process. So we just assume the mining process spend a fixed time. The latency defined from the transaction lifecycle can reflect the latency of the interaction between different nodes, and also the block-oriented latency can reflect the latency of block transmission. Then let's look into the transaction-oriented latency and block-oriented latency. We conclude the workflow of 2 types of latency from the guest log. First, for the transaction-oriented latency, if a user submits a transaction in node A, the transaction will first wait in a queue in node A, and then it will be promoted and verified by node A. If it is verified legal, the transaction will be formally submitted, and then transferred to node B. Also, when the transaction arrives at the node B, it also waits in a queue, and will be promoted and be verified by node B later. Then, after the verification, the transaction will be further transferred to other nodes. We define from the transaction submission in node A to the transaction being promoted in node B at the transaction-oriented latency. Well, because 2 devices have different system time, and guests will record the system time of different operations in the guest log. We need to synchronize the system time between 2 devices before run the experiment to get accurate results. Second, for the block-oriented latency, the mining node spends some time to mine the block. After a block is mined in the mining node, it will be immediately transferred to node C. Similar to transactions, when the block arrives at node C, it also waits in a queue, and will be imported and processed by node C later. In the process, the node C will first further transfer the block to other nodes simply after the block header is verified, in order to propagate the block to the entire network as soon as possible. After that, the block C will verify the block body and insert the block in the local storage and announce to other nodes that the block C has already owned the block in order to reduce redundant transmissions. We define from the block is mined in the mining node to node C import the block as the block-oriented latency. Also, the same with the transaction-oriented latency. We need to synchronize the system time of 2 devices to get accurate results. Then, is how we can measure the two types of latency. For most IoT devices don't have enough power to mine the block, so we introduce the powerful mining node and build a linear structure with IoT devices to evaluate latencies. We first synchronize the system time of those 5 devices, then deploy and run the gas. We then deploy a smart contract in this blockchain network and send transactions from all deep nodes to call the smart contract. After experiments, we collect gas log from 5 devices and extract timestamps of the target operations. Finally, we calculate the latency with those timestamps. The third part is how we evaluate 2 types of latency with the real deployed blockchain network. We set up our experiment structure with the laptop and 4 Raspberry Pi 3B Plus. The configurations are shown in the right. All of those nodes are connected to a Wi-Fi router, which is the underlying network. The average RTT from the laptop to other Raspberry Pi 3B Plus is about 5 milliseconds. We then first synchronize the system time of those 5 devices to the NTP pool in Japan with NTP date. Then we deploy a smart contract to record string, and we use Web3GS library to call the smart contract constantly from every Raspberry Pi 3B Plus. Then we measure 2 scenarios with this structure, baseline and realistic scenarios. First is the baseline scenario. The baseline scenario shows the latency when transmitting the minimum workload of transactions and blocks. For the transaction-oriented latency, we send 1 transaction from every date node, and those transactions are propagated to the mining node. The result shows that the average latency of sending 1 transaction per hop is about 9 milliseconds. And for the block-oriented latency, we send an empty block from the mining node to the date node. An empty block is about 539 or 540 bytes, and the average latency of sending 1 empty block is about 34 milliseconds per hop. Second is the realistic scenario. The realistic scenario shows the latency when transmitting transactions and blocks with some workloads. For the transaction-oriented latency, we send 10 and 100 transactions from date nodes once a time. We can collect the data from the gas log in each node, which reflect the interaction between different nodes. Because no transfer transactions to the next node without waiting for all transactions being received. So we can see in the figure, especially when transferring 100 transactions, the first hop spent about 200 milliseconds, while the later hops spend about 60 milliseconds more than the previous hop. And we can also notice the latency of transferring 10 transactions is not 10 times of the latency of transferring 1 transaction. The latency of transferring 100 transactions is also not 10 times of the latency of transmitting 10 transactions. Then we mine those transactions and send block back to date nodes, which is the block-oriented latency in realistic scenario. First, compared to the baseline scenario, transferring a block with 1 transaction inside the block spend 40 milliseconds more than transferring an empty block. Second, we can see from the figure, the first hop of transmitting a block with 100 transactions is about 150 milliseconds, and then the later hops spend about 50 milliseconds more than the previous hop. The reason is because Ethereum deals with block header and block body separately. Finally, we add the average value of the transaction-oriented latency and block-oriented latency together. It shows the overall latency on transmission in transaction lifecycle without the mining time, which is the latency for data nodes to interact with the mining node in different hops. We can notice that for 1 and 10 transactions, the block-oriented latency is larger than the transaction-oriented latency, while for the 100 transactions, the block-oriented latency is smaller than the transaction-oriented latency. At the end, we make a conclusion on our work. The blockchain technology can combine with IoT to solve some challenges, so understanding its performance is essential. To better evaluate latency in private blockchain network, we define two types of latency according to the transaction lifecycle, which are the transaction-oriented latency and the block-oriented latency. The latencies concluded from the transaction lifecycle can reflect the latency of the interaction between different nodes, and the block-oriented latency can reflect the latency of transmitting blocks of different size. We then characterize the two types of latency in a real private blockchain network in two scenarios, which are baseline scenario and realistic scenario. In the future, we plan to measure the latency performance with a more complex structure, then accept the proof of work algorithm. Ethereum also provides a proof of authority algorithm, which is also suitable for the private blockchain network. We also plan to characterize the latency in proof of authority network. And thank you very much for listening.
Hello everyone. Today I will talk about energy minimization for UAV-enabled video relay system under QoE constraints. First, I will introduce the background. In recent years, mobile video streaming has been dominating the global mobile data traffic. However, the QoE of end users will be degraded due to the increased congestion brought by the growing popularity of video service, especially the cell edge users. As a result, recent researchers have paid more attention on developing efficient solutions to meet the user's QoE requirement. Recently, UAVs are introduced for providing wireless video service as a relay node in infrastructureless areas by relaying data from remote base stations. With UAV-enabled relay system, line-of-sight channels between the UAV and ground users can be established mostly, and the UAV can adjust its location swiftly to serve the ground users flexibly. However, due to the high mobility of the UAV, the channel quality varies over time. To tackle such challenge, Dash can be adopted in the UAV-enabled video relay system. That is the HTTP adaptive video streaming. With Dash-based video streaming, the streaming media is able to select the most suitable video bitrate dynamically based on its instantaneous channel quality. To be specific, Dash can adjust the quality of the video based on the transmission rate or available bandwidth between the UAV and the ground users. Although Dash is adopted, UAV-enabled video relay system still faces new challenges. First, the UAV unit has very limited endurance due to the limited onboard energy. Compared to the conventional terror base station, UAV flight, for example, hovering or flying, incurs additional propulsion energy consumption. Second, the UAV location should strike a balance between the base station to UAV, that is the B2U channel quality, and UAV to ground, that is U2G channel quality. As the increment of U2G channel quality is generally at the cost of decrement of B2E channel quality. Furthermore, the communication resources should be efficiently allocated. For example, the UAV may transmit to the closer ground users with more transmit power to better exploit the channels. Most of the existing studies about UAV relay network focused on the performance analysis about the case that there is only one source and one destination for the UAV relay. Furthermore, the existing works about the UAV-enabled relay did not consider the UAV endurance due to the limited onboard energy and QoE constraints introduced by video streaming. To provide energy-efficient video service for ground users in UAV-enabled relay system, the total energy consumption of the UAV should be minimized, while ensuring the QoE requirement of ground users by joint design of bandwidth and transmit power allocation of UAV, as well as UAV trajectory, which is the main focus of our work. We consider a scenario where the established base station of wireless access is not functioning. Such area may be a remote area, where there is no direct links between other base stations and the ground users. There are M existing base stations and K ground users in such area. A rotary wing UAV is employed as an error relay platform to provide video service from existing base stations to multiple ground users. The UAV is assumed to fly at a constant altitude of h. FDMA scheme is adopted by the UAV, with dynamic bandwidth allocation among all base stations and ground users. In particular, at any time not during the UAV flight period, the UAV communicates with multiple base stations and ground users simultaneously by assigning each base station or ground user a fraction of the total bandwidth. For example, XMD denotes the fraction of the total bandwidth that is allocated for the base station SM, and YKT denotes fraction of the total bandwidth that is allocated for the ground user UK. The B2U channels are assumed to be dominated by the naive side links, and RMT denotes the normalized instantaneous achievable rate of base station SM and B2U communication in time slot T, which is calculated as this. For U2G channels, single reflection and scattering occurs in air-to-ground communication links, which are modeled as feeding channels. The approximation of the average rate for U2G link is calculated as this. We model the QoE utility as a log function with respect to the video transmission rate. The constant theta and beta are positive and different for various types of applications. RK is the required playback rate for user UK. RK bar is the time average transmission rate for ground user UK. The energy consumption of the UAV consists of both communication-related energy and propulsion energy. The communication-related energy of the UAV can be calculated as EC, and the UAV's propulsion energy can be modeled as a function of UAV speed. Given the location of ground users and base stations, we should determine the UAV's trajectory and how to allocate the bandwidth and transmit power among all ground users and base stations. And our objective is to minimize the total energy consumption of the UAV, while ensuring that the target QoE utility of each ground user is achieved. Based on the various models derived above, the optimization problem can be expressed as P1. In P1, constraint 3 are the information causality constraint, where the sum of data rate for U2G links should not exceed the rate for B2U link, and PU is the maximum allowed transmit power. It can be verified that problem P1 is a non-convex problem, which is difficult to be solved directly. So we propose an efficient method to obtain a suboptimal solution by utilizing alternating optimization and successive convex approximation, that is SCA, techniques. The key idea is that we consider the two subproblems of P1, that is the transmit power and bandwidth optimization problem with a fixed UAV trajectory. And the other subproblem is the UAV trajectory optimization problem with fixed transmit power and bandwidth. The two subproblems are optimized in an alternating manner until the object value converges. Let's first see the first subproblem, that is the transmit power and bandwidth optimization. By introducing slack variable omega kn To denote the relay's transmit rate, it can be verified that P3 is a convex optimization problem, which can be solved efficiently by standard convex optimization solvers or existing software such as CVX. Now let's see the second subproblem. That is the UAV trajectory optimization problem. That is P4. P4 is still a non-convex optimization problem due to the non-convex constraints in 13 and 14 and the non-convex objective function. To tackle such difficulties by using SCA technique, non-convex constraints 13 and 14 as well as objective function are replaced by more tackable constraints at a given local point in each iteration. To be specific, by introducing slack variable tau t, EP is now joint convex with respect to Vt and tau t, and P4 can be written as P6. With given local point QRT in the rth iteration, by applying the first-order Taylor expansion of convex functions to obtain lower bounds, P6 can be approximated as P7. As a result, P6 can be solved by optimization P7 iteratively. Using the results obtained above, we propose an overall algorithm for computing the suboptimal solution to problem P1. By employing SCA and alternating optimization techniques, the details of the proposed algorithm are summarized in algorithm 1. And we can prove that the proposed algorithm 1 is convergent. Now let's see the simulation results. For the simulation settings, the ground users are randomly distributed in a square area, and the two base stations are located at the left side and right side of the area respectively. The parameters are set as the table shows. The performance metric is the total energy consumption of the UAV. Now let's see these figures. The optimized trajectories and UAV speed with different QoE requirement U-bar when the total time slot is given as 120. The square denotes the initial and the final UAV locations, and the triangles denote different existing base stations. It is observed that with the increase of U-bar, the UAV will adjust its trajectory to move closer to the base stations to obtain more video data, and then move closer to or even hover over ground users to provide better video service, as expected. When U-bar decreases, the trajectory shrinks, and mainly consists of smooth curves. If U-bar is sufficiently large, the UAV tends to fly over each base station and ground user with the maximum speed. This is expected since for satisfying large QoE requirement, the UAV should fly to approach the base stations and ground users such that better communication channels can be achieved. And these figures reflect the transmit power and bandwidth allocation of the UAV. We can see that the UAV only relay video data when the UAV moves closer to the corresponding ground user, and the bandwidth is allocated to the base station if the UAV moves close to it, such that more video data can be obtained. Finally, we compare the UAV's total energy consumption between our proposed scheme and three benchmarks. We can see that the proposed schemes can achieve lower energy consumption of the UAV than other benchmarks. And the gain comes from the joint design of resource allocation and UAV trajectory. The energy consumption of the UAV increases when U-bar increases, since the UAV needs to hover over each ground user so that better video service can be provided. Now let's conclude our paper. We consider a UAV-enabled video relay system to minimize the UAV's energy consumption while guaranteeing the QoE constraint of each ground user. By joint optimization, the bandwidth and transmit power allocation as well as the UAV trajectory. We propose an efficient iterative algorithm to obtain a KKT solution by solving the two subproblems with successive convex approximation, that is SCA, and alternating optimization techniques. Simulation results demonstrate that with the proposed joint design, the UAV's energy consumption can be significantly reduced by up to 30%. The proposed design framework is general and can be applied to joint design UAV trajectory and resource allocation in other UAV-enabled video streaming systems. Thanks.
Okay, everybody. In this topic, I will give the discussion about adaptive handover scheme for multi-mode device in power wireless heterogeneous network. This paper is written by several authors, and the main authors they come from the smart grid of China. In this topic, our discussion includes 5 parts. The first motivation, we will give why adaptive handover scheme is necessary for power wireless heterogeneous networks. Second, we will give the system model. Third, we will give the problem formulation and the optimal solution. And in the following, we will give the simulation results and the discussions. Finally, we will conclude this paper. Let's go to the first part, motivation. We know in the last several years, the increase in traffic, especially videos, has been the main traffic of the wireless networks. It seems and the same thing happens in the smart grid, such as video surveillance has put much great challenge on the capacity of wireless smart grid. In smart grid of China, they also focus on the small cell networks, and they want to build some specialized wireless networks for the wireless data transmission. Small cell networks are one of the promising solutions to meet the increasing demands. However, we know that there are many small cells, especially in the 5G networks. The network cells become more and more smaller, and if the user travel in space, the handover may be frequently, and in addition, the cost of deploying high-speed backhaul may hinder the densification of network. In this scenario, we do some work in this paper. First, we introduce caching and transmission into the small cell networks and investigate the cooperative caching and transmission problem for the videos. About the videos, we investigate the SVC encoded scheme. Second, we formulate the video delivery delay minimization problem. In our scheme, the users will travel, and we aim to deliver the video in a high efficiency to the users. And for the SBS means the small cell networks. And since the small cell network are smaller and they have some overlapped coverage space, and the video delivery minimization problem, considering the overlapped coverage of SBS and the limited backhaul capacity. About to solve the problem, we design a two-stage algorithm. In the first stage, a greedy caching algorithm is designed to catch the video with encoding layers at each SBS. At the second stage, we design a content delivery algorithm to decide which place should serve the demands of users. And that's our motivation and contribution. In the following, we will go to the system model part. In the system model part, we first give the network background. From the slides, we can see the heterogeneous smart grid network. In this network, a macro base station is connected with a remote video server, and MSBs are deployed densely to serve N wireless users. Denote the SBS set as M and the users set as N. The SBS are connected with MBS via backhaul link, and through which the cached contents can be shared to avoid requesting these contents from remote servers. And for the video request, we also have a key cooperation strategy, and we will describe the strategy in the later. And first, we will give some sentences about the scalable video coding and caching. In our network model, the SBS are equipped with a cache of size cm bits, and this which is filled in advance during off-peak hours, according to the popularity of the videos. Each user independently requests videos of interest from our library of VSet, and each video has the same size. We utilize SVC, scalable video coding, to encode each video content into multiple layers, and the multiple layers are denoted by set L. And the combination of these layers can achieve a certain quality level of corresponding video. For example, layer 1 provides the basic quality level 1, and the level 2 and the quality level 2 can be achieved by adding layer 2 and so on. Typically, the quality level Q requires all the lower layer 1 to Q successfully decoded. We use L to represent the layer L of video V, and VQ to represent the Q's quality level of video V. The size of layer LVL is denoted as S. Okay, let's go to the request and cooperation part. In this part, we assume the probability that users request the Q's quality level of video V is known in advance, denoted by P. And as mentioned before, when the user requests a video with quality level Q, all the layers below Q must be successfully received. To reduce the download delay, those layers are sent to the user at the same time. Thus, the delivery delay of video is bounded by the maximum delivery delay among all the layers, which is denoted by DNVQ. And in order to efficiently utilize the limited cache size of SBS, the cached contents in SBSI can be shared with SBSG through the backhaul link. And we can go back to the figure 1. The user 3 request for video V12, and the layer L12 hasn't been cached in its nearby SBS. And then the SBS with the layer L12 will send it to the nearest SBS of user 3, which will reduce the download delay compared with fetching L12 from the remote server. And according to this, we can conclude our video request or content request scheme as the following mode. The first, local delivery mode. With this mode, it means the content are stored in the nearby SBS. If in this case, the user will get the content from the nearby SBS, and the download rate of this mode is given by the Shannon equation, which is denoted by the second function. We also have the backhaul delivery mode. If in this case, if the requested content of user N hasn't been cached in SBS in the nearby SBS set, and then the nearest SBS of user N will attempt to fetch this content through backhauling and send it to user. This process will cause a larger delay compared with the local delay. We use KB to denote the download rate, where key represents the SBS that sends the requested content. The last mode is the remote delivery mode. If the content or the requested content is not in the nearby SBS or the MBS, and the requested file will be fetched from the remote servers, and this fetching will cause the slowest download rate at 0. After giving the background, and we will give the problem formulation and the solution. And we know in this paper, our goal is to minimize the download delay of video with different quality level, and design adaptive handover scheme. And we first give the cache size constraint of SBS, which can be expressed by the third function. And the download rate in local delivery mode should be larger than backhaul delivery mode, which is denoted by the fourth function. The delay for user N receiving the layer LVL can be pressed as the fifth function. In this function, we have the we include all the three delivery modes. For the first is nearby delivery mode, the local delivery mode, and this is a remote delivery mode, and this is a nearby delivery mode. The upstream traffic of SBS cannot greater than its backhaul capacity. And we can have the delay for user N receiving the layer LVL, which can be denoted by the our function 7. And the 7 is our objective function. It aims to minimize the delay for user N, for all the users to get their required content. And we can also obtain from this function that the users can travel in speed, and they can hand over when our scheme decides that they should connect to other SBS or MBS. And then we will go to the solution part. In our solution, the problem is NP hard, which can be proved by reduction from the knapsack problem, and later can be expressed as follows. And to solve this problem, we give a two-stage algorithm. And in this algorithm, we include some two sub-algorithms. The algorithm 1 is greedy layer caching algorithm. In this algorithm, we can obtain or decide how the content can be cached on the SBS. And the second is the layer caching and cooperative delivery algorithm. In this algorithm, we will consider how to deliver contents to the users. And we also consider that the SBS have overlapped coverages. And finally, we will go to the simulation parts and our discussion. In our simulation parts, we have six figures, and we group the figures into two groups. The first is figure 2. In figure 2, we have three sub-figures, which are A, B, and C, respectively. In figure 2A, in these figures, we compare the impact of different caching schemes on the average delivery delay. And with the default value CM 20%, sigma 0.3, and BM 20, it can be seen that our proposed algorithm always achieves the minimum delivery delay. This is because the MPC redundantly caches the most popular content in each SBS, ignoring the cooperation opportunity between SBS. And this can be seen from figure 2C. The increasing of backhaul capacity has no impact on the delivery delay in MPC. Although LCDs caches different contents as much as possible, it doesn't consider the popularity of the content. Thus, from figure 2B, the increasing of the parameter sigma has no impact on the delivery delay in LCD. And in Octopus, each user is only associated with the closest SBS, ignoring the overlapped coverage of SBS, which leads to a larger delivery delay compared with our algorithm. In addition, we can see that the marginal value of catching new content becomes smaller as the cache size increasing from figure 2A. Therefore, we should catch the content with more delay savings when the cache set is small. From figure 2B, the average delivery delay increases with the increasing of the CF scrolling parameter sigma, because the popularity is more concentrated in a few videos with larger sigma. From figure 2C, as the backhaul capacity increases, the delivery delay decreases, because the SBS with larger backhaul capacity can share more cached contents, thus avoiding fetching them from the remote server. And we will go to another figure. Figure 3 compares the impact of different caching schemes on backhaul traffic load. It can be seen that the MBC scheme always achieves the minimum backhaul traffic, because there is no cooperation between SBS in MPC, thus reducing the traffic caused by sharing contents over the backhaul content. However, as can be seen from figure 2, MPC will result in the largest delivery delay. LCD tries to catch more different contents, which results in more frequent sharing of cached contents, and it achieves the maximum backhaul traffic in figure 3. Our proposed algorithm has smaller backhaul traffic compared with Octopus, because the users only associate with the closest SBS. The cached contents in the nearby SBS should be delivered through the backhaul link, which results in lead to a larger backhaul traffic. In particular, we can see that Our proposed algorithm has a large gap between octopus when catch size is smaller from figure 3a. Finally, we will conclude our algorithm. We designed a cooperative caching and transmission strategy for video layers encoded by SVC. We formulated a problem to minimize the video delivery delay, and we designed a greedy algorithm with a two-stage scheme. And thanks everybody, and that's our presentation.
Hello everyone, I'm MONAMI. My paper is a novel displacement estimation method of ultrasound elastography for telemedicine. Traditional medicine relies on palpation to feel the size, shape, or firmness of soft tissue, which can provide evidence for the early diagnosis of needles. The traditional ultrasound imaging method provides a reflection of the acoustic impedance of soft tissue. The ultrasonic elastography method is different from it, in that it can reflect the physical information of soft tissue through images. Ultrasound elastography has become a research focus because it can accurately measure soft tissue lesions. Displacement estimation is a key step in ultrasound elastography. The phase zero search method is a popular displacement estimation method that is accurate and rapid. However, the method is ineffective when the displacement is more than a quarter wavelength. The block matching method can address this shortcoming because it is suitable for large displacement, although it is not accurate. Notably, the quarter-guide block matching method has exhibited good robustness under complex mathematical conditions. So in this paper, we propose a novel displacement estimation method that combines the block matching method and the phase zero search method. Next, I will talk about method. The quality-guided block matching method does not calculate the blocks in the target frame in the order of room and column. It calculates the displacement of its neighbor block by referring to the block with the highest matching degree at a given point in time. Using this method can ensure that the more matchable block gets calculated first, and the block that has more noise and easily results in error is computed last, thus avoiding the transmission and accumulation of errors. The steps of method are as follows. Step 1. Select the starting block A and put it into the set S to calculate the displacement and matching degree. Step 2. Find the most matchable block in set S and take it at the current block. If there is more than one candidate, then randomly select it from the candidates. Step 3. Compute the displacement and matching degree of the current block. Step 4. If there are neighboring blocks of the current block that have not been computed, go to 5, otherwise go to 7. Step 5. If the neighboring block chosen in the last step was not in sight, initialize the neighboring block with the displacement and matching degree of current block, put it into set and go to 4. If it was inside, go to step 6. Step 6 is if the matching degree of neighboring block is higher than the current block, go to step 4, otherwise update the displacement and matching degree of the neighboring block. On step 7, remove the current block from set S. Last, if set is not empty, go to step 2, otherwise the steps are finished. Now, let's talk about phase zero search. The phase zero search first calculates the identical form of the two frames of single before and after palpation. It calculates the position of the phase zero crossing by using the cross correlation of the analytical singles, such as the potential of the max value of the cross correlation function. This method can obtain equal accuracy with oversimplifying by a level calculation and accused phase cancellation, resulting in the miscalculation of time delay when the displacement is more than a half phase. So we propose my method. The method is as follows. Combining block matching with a phase rule search can obtain an acute displacement field after first computing a rough displacement with block matching that limits the error no more than a half phase to clearly reflect the physical characteristic of the tissue. We compute the strain field from the displacement field with the Gardner method. Now, let's take a look at my experimental setup, including used software, experimental setting, and so on. Now let's talk about contrast method. Now the main daily estimation method include normalized across correlation, correlation coefficient, sum of absolute difference, sum of squared difference, proportion of leap correlation and Hibbeson cross correlation and mirror space methods. The correlation of singles is strong and high single noise radio. So the performance of all methods is similar. With the decrease of single correlation, the performance of different methods decreases to different degrees. And then the performance of normalized cross correlation methods is optimal. In practice, combined correlation method by using multi-autocorrelation process units in parallel, it should be possible to perform real-time processing similar to traditional doubling methods. The two contrast methods is time delay estimation. The present TDE method has good performance on the high single-to-noise radio. However, by the decrease of single correlation, the performance decrease, so the result is poor. Time delay estimation is used to calculate the time delay of reference single and contrast single in a period of time. The time shift axis between the reference single and the contrast single. Now let's talk about my experiment about estimation of longitudinal displacement. In the TDE method, RF single are intentional oversleepment. When looking for the peak of the cross-correlation function, the parabolic interpolation method is adopted. Figure A, B, and C show the displacement field calculated by the TDE method, the CM method, and our method. And Figure D shows the comparison between the displacement distribution of three methods of longitudinal and the displacement distribution. It can be seen that the method in this paper is close to the real displacement distribution, because the method in this paper takes the displacement of neighboring points and the peer information. When calculating the displacement of certain point, which not only improves the accuracy but also greatly reduces the search scope. So, reducing the amount of calculation and speeding up the calculation speed to obtain the same results as the method. The TDE method needs to carry out oversleeping with a very large amount of computation. There are also many redundant cross-correlation calculations in the CM, and the half-wavelength limits cannot be broken. To quantitatively analyze the accuracy of three methods, this is define the displacement difference of the calculation results. So These results are shown in table. The displacement field area of this method is the smallest, which indicates that calculation results of this method is more accurate. This is shown in figure. The method in the paper is close to the real displacement distribution. Now let's talk about the strain estimation. To clearly indicate the physical characteristic to the tissue, we compute the tissue strain on the basis of the displacement field to the least square method. The time strain to represented by a gradient. Figure A, B, and C represent the results to the TD, CM, and R method. As seen from the figure, the results obtained by the method in this paper too similar, and this tissue is easier to distinguish. Figure D shows the strain distribution at the medial position. A comparative transport rate is adopted to quantitatively analyze the lesion degree resolution of the tissue of each method, while MB30B are the mean and the standard deviation of the background, and MT30T are the mean and the standard deviation of the target. These are shown in table. The CR of the three methods are calculated as follows. Otherwise, after computation, CF of method is highest, which is the same as shown in figure. Now let's talk about limited and future work. Our paper presents a new displacement estimation method for ultrasound elastography, namely the QJBM and the PS method. The experimental results show that our method can calculate and efficiently calculate the displacement field and efficiently solve the error transmission problem when using peer information. In the future, this method will be further optimized. For example, in the QBBM, the determination of block size can be adaptive. In the PS method, the results can be calculated by an iterative method to make the results more accurate. And the GPU error can be used to accelerate the method to meet real-time requirements. With the development of modern communication technology, telemedicine using mobile device or the internet will become more population. So that's all. Thank you.
Good morning, everyone. Welcome to the N2ME meeting co-located with the MONAMI Conference 2020. Thank you very much for taking a valuable time. I'm Xun Zhao, the mentor of Wen Zhu, who is the winner of the N2ME Fellowship. The topic is how to better prepare for academic career. So let's give the time to Wen Zhu and the panelists.
Thank you for all coming to this event. We are pleased to organize this N2 Women for the first time at MONAMI's conference. And let's begin. Our first topic is focuses on how to get effective rest. Yeah, someone once said there is no one who do good job without a good rest. For me, I have tried many rest methods such as singing, dancing, meditation, etc. But in most cases it failed. I always think about my study unconsciously, and the pressure is always with me, which also causes my life to collapse once in a few days. So here my first question comes. How do you usually relax yourself? And so I started with Xi. Can you share your experience with us first? Thank you.
Yes, thank you. Yeah, I think the purpose of doing things for a good research is to do a good job. But yeah, the doing things to for a good rest can temporarily forget the pressure. But after that, you should face the problem again. So I don't think doing things can really reduce the pressure, but just temporarily forget the pressure. So what can really reduce the pressure is to find the problem in your research and find the way to solve the problem. And that's my experience. Yes, I don't think doing things can really reduce the pressure, but just face the problem and find ways to solve the problem. That's my experience.
Thank you. Learning it just temporarily.
Yeah, temporarily.
Yeah. Okay. And what do you think about this? Tian Kangwei? Yeah. Thank you. Yeah.
Yeah. Hi. Are you speaking to me?
Yes.
Okay. Right. Okay. Talking about pressure and PhD journey, I was thinking, I could offer like 3 things. Keep it short. It is FAR, F-A-R. Okay. Where F stands for being focused. So when you have a lot of things to do, and when you thinking about your research and the dissertation, being focused is very important. Being focused not just about focusing on doing the thing that you said, doing something to forget about it, but then it's like focus on your plan. So I find it very effective if I were to jot it down. It doesn't matter whether my thoughts are haphazard or whether I am really sure about doing certain things. I just list down all of them and start prioritizing and start looking at maybe these are the things that I can drop off and these are the things that I should spend more effort. So if you have a plan in mind and you can keep focus on a certain areas or certain items that is important. And that leads to the next one, A, F-A-R-A. That is, you need to know your aim. So if by having that list, then which are the ones that eventually drive you to your aim? So knowing your aim can be very large. It can be, why are you doing your PhD in the first place? Because that gets you far. You see, you have to focus on your aim to get you far. The other one, aim can be immediate. So you have different levels of aim. You can have your far aim, which is why are you doing PhD in the first place? And the other aim could be very near term. What do I aim? Do I aim to finish a certain milestone, a paper at the end of this year, or do you have qualifying examination? It's your first year. If you have qualifying examination, when are you going to finish the qualifying examination? If you're going to finish qualifying examination in 1 year, you can set then your aim in a half a year to be finish 15 papers, for example. So it is really what is your aim, what is your long-term aim, and what is your short-term aim. That's my thing. The last one that I thought I would like to share is R, which is being resilient. Resilient meaning you will definitely get setbacks. In my 6.5 years of PhD, I did it in part-time mode. So there's really lots of rejections from conferences, rejections from ideas, rejections from even peers, when you're discussing about something, they say, oh, why don't you do that? And why don't you do another thing? So it's just really being resilient to changes, resilient to rejections, and resilient to setbacks. Because it's not that you're not doing well, it's just that the different people have different opinions. Yeah. So my advice is really focus, knowing what is your aim, your long-term aim and short-term aim, and being resilient as the process of going through it.
Yeah, thank you. That's really inspiring. And for you, I think your PhD experience must very happy and yeah. And there's another question in my mind is when there is a research problem for you cannot be solved, how do you deal with the pressure? Yeah, research pressure.
Okay, so back to are you still you're talking to me, right? So definitely we get roadblocks, okay, and difficulties during our PhD period. I faced it multiple times. I even changed my dissertation topic in between. Yeah, I even have a change in my dissertation topic during my PhD days. So it is not about, there is definitely pressure, but being resilient means that going around the problem. Like it could be a certain method that I was trying and it's not working. Can I try another method? Can I have some ideas from other fields? So it can be, if I can, I do a lot of healthcare research. So I draw inspirations from a varied literature, not just in healthcare, not just in optimization. I look at further, it could be from other domain like manufacturing. It could be something out there that you could have a change and tweak it to apply to the domain in which you are studying.
Okay.
Changing an angle, being resilient.
Maybe she can
answer the question.
I think it is a little difficult for Wen to get your point very precisely, but I suggest her repeat this meeting video again and again.
Okay, thank you. And this year is about Tencon and how about you is red hacking?
Hello, I'm here.
Yeah. How do you really relax yourself?
Can you repeat your question, please?
I say, how do you usually relax yourself?
Okay, that's very interesting question. So this pressure is always there when you are a grad student or when you are at workplace, like in academia or industry. Pressure is always there. So you have to have your own approach to take care of that. So you should figure out that, what do you like to do to relax yourself? So for example, what I do after a long day of work, instead of driving back home, I take bus. And the reason is if I take bus, it takes me like 45 minutes.
And during this time, I actually listen music. And half of the time, like, I listen music, and also I walk. I walk for like, let's say 1.5 kilometers. So this is something really helpful for me, to get out of the stress. And then, this is something I regularly do to make sure that, whatever I do during the daytime, I take my own time and then, do whatever I like to do, maybe listening music or walking or biking, and then forget about all the work, all the pressure. And then once I'm done with all this relaxing thing, then actually, I get full energy, and doesn't matter the problem that I'm taking care of is really hard, or I have like, so much work to finish. I feel that, yes, I can do it because I'm like fully energized after that relaxing part. So yeah, this is something I do. And also sometimes I talk to my friends and colleagues. Like, let's say sometimes I'm like really, really down or frustrated or like, stressed out. Sometimes, I have a couple of really good friends and mentors. So sometimes I, try to talk to them. And guess what? I figure out that I'm not the only one face those challenges or issues. They also face, and they share their opinion. And that's actually really, really helpful. So yeah, these are some sort of useful approaches that you can use. But let me just add one more thing. In my opinion, time management is very important, both in academia as a student or faculty or in industry. So most of the time, if you can manage your time for different tasks, for your research, for paper writing, for exams, so on and so forth, I think that reduces a lot of pressure that can create stress later on. So if you can manage your time, sometimes you will see that you can solve some of the problem before it can even happen.
Thank you. Thank you very much. Okay, we have temporarily forget it, and if AR method and do something you like. I want to know, Nirushan Fernando, what do you think about this question? Yeah.
Yeah, I think I guess it depends on what would work for you. So if I can share something that I experienced. So in my first year as a lecturer, like after my PhD, so after some time I got a full-time position as a lecturer, and then I was really, really stressed because I had to manage my teaching load and my research load, and I was having a very hard time to, relax. And when you are stressed, you're also not performing at your best, right? Because you're always constantly worried about, I have these things to do, and so on. And then I was looking around, and there were these professors, and they seemed to be, managing it really well. And I was like, I felt that I must be doing something really wrong. Like I felt really inadequate, like I'm doing something wrong. And then I talked to someone, and at that time she was an associate professor, and she was doing very well in research. And I asked her, how do you manage all these teaching loads and research loads, and how do you keep relaxed, and how do you make it easy? And she said, oh, it's not easy. It's hard for everyone. And and she said that, even for her, it's really hard. And that helped me, because she didn't give me a solution. She said, I don't have a solution, even I find this hard. But that helped me, because then I saw that, these things are not easy to manage for anyone. So we all have this challenge to, of managing pressure and managing stress. And so it wasn't that I was doing something wrong. It's just that process of talking to someone and sharing their experience that helped me. And then after that, I was more relaxed. So it wasn't like, oh my gosh, I haven't done this, I haven't done that. It was more like, okay, so maybe I wouldn't be able to spend 5 hours, giving feedback to students. Maybe I try to, prioritize what's the best thing that could help them instead of, overwhelmingly spending so much time. So I think just sometimes talking to someone who has done it before can help, just to understand that it's a shared challenge, that you're not alone in trying to find a solution.
Yeah, thank you, yeah, for your advice. And for me, I also think it's not easy to rest. But now I will do my best in my PhD time. And I'll move to the second topic. It's about work-life balance. I have seen some other N2 women discussions. It's about finding work-life balance is a myth. I think it's a very interesting topic, and it also bothers me. So can work and life really be balanced? I will say myself, for me, the answer is of course not. I think it's impossible. Work and life really can be balanced. For example, my boyfriend and I are in a long distance relationship. We can't see each other often, and we can't have dinner together or watch movies like other couples. And I also can't go home often, even if I am even if I'm at home. Friends and relatives tell me to go shopping or have a dinner. It is okay at first time, but the third time for me, I must formally refuse them because I have to leave enough time to get with my studies. So I'm particularly curious, how do you balance the relationship between the two, between work and life? Are the measures effective? I'm sorry, Fernando,
Yeah.
How do you see?
For me, I think I think I've never been able to have 50-50 to work and life at the same time. It's always been like at sometimes, I give more to work, and sometimes I give more to my relationships and family. So it's it is challenging, particularly for women, I think, because women traditionally we seem to be doing more domestic things, and also I have a son, I have a toddler, and so when you have children also, then it's not easy because they demand a lot of attention as well. So, but for me, what works is, at times I know that I have to give more focus to my, my husband or my son or my parents to do those things with them. But sometimes when I'm, for example, I might have a deadline for a grant or some important thing in my work, and then I might actually spend more time at work in those situations. So it's kind of like a juggling act, I guess. It's for me, it hasn't been about always being balanced across. yeah, it's kind of like figuring out, yeah, but at the same time though, there are things that you always have to do, right? So you have to figure, like, prioritize what are the important things that I can't miss. Like, I know for me that I try to spend at least a couple of hours with my son every day. You know, so that's something that I wouldn't miss. But there are some other things, like, so, you know, I might not be able to make a, you know, a really elaborate home cooked meal every day, because I might have to spend some time, extra time on doing, you know, working on a grant or working on a paper on some days. So figure out, I guess, what things that you can, you know, do without on certain times, at certain times or certain days. And then, yeah, and then figure out the things that you need to do every day. And then it's a matter of, I guess, you know, kind of like juggling.
Yeah, it's difficult for everyone, especially for us. Oh, yeah.
Yeah.
Thank you for your sharing. And so, what about you? How how do you balance the relationship between work and life?
To be honest, this problem is still bothering me until now. Yeah, and it becomes more serious after I start to work. As a PhD student, I only need to consider myself and research. But after job, I have to consider my family, my husband, my daughter, and also education and research. I have more things to consider. And so this problem becomes more serious. And I think I spend more time for work. But I would like to spend more time for my family, but I can't because we are living in a foreign country, and the grandfather and grandmother didn't live together, so they can't help me to take care of my daughter. I have to take care of all my children by myself. So
That's a good question.
Yeah, maybe after your graduation, you will understand me. Yeah, so at least a moment I can say I can balance work and life, but I just do the things that is more urgent. Yes. So this is the current situation for me. I also bothered for this problem. Yeah, so I would like to listen to other professors how they balance the work and life. Actually.
Okay.
Yeah. Yes, thank you.
Okay, thank you. And then I start this question to Tian Kawei. Hello. Yeah. How do you balance work and life?
For me, it's a combination of time management, which is time management as well as understanding from family. My situation is quite interesting as well. Of course, I have 3 kids. 3 kids within 2 years. So I have a daughter. I gave birth to her 2 years into my PhD, and I gave birth to a pair of twin boys, 2 years later. So I have 3 kids in within 2 years of time frame. Yeah, so I would say time management, balancing, indeed, it wasn't too easy. It's not a bed of roses either. What I've done during my PhD days is to really understand myself. When is my most productive hours? So I'm a very morning person. When is my most productive hours? The period of time in which my brain can process faster and therefore have a better output. So I came to realize that I am a very morning person. I tend to think very fast, well focused at 4:30 a.m. to 7:30 a.m. and none of the children are awake.
Wow.
So if I were to wake up at 4 o'clock or 4:30, this morning I was up by 5. So I finished a couple of things before this meeting. Yeah, so I have already have a 3-hour focus time on work when the whole house is quiet. Yeah, so that is what I've done. And then I kind of like trade off when I need, so after that, I need to send my children to childcare or school. In the evening, I need to pick them up, I need to spend some time with them. I have that pocket of time because I already have some early in the morning. So yes, there is a little bit of a sacrifice in terms of sleep. But I tend to sleep a bit earlier together with the kids. Right now, my kids are 11 and 9. I also find it, in fact, the juggling did not stop. It got harder because the demands from their schoolwork, the demand from many other aspects has been increased because they have classes, they have extra classes, exercise, sports activity and so on in school and other activity. So if I were to, so I will have to plan my time, and also when it comes to coaching the children, I apply what I did to my students to my children as well. So at work, I would have set aside office hours for my students. So I said, office hours for my students, you're allowed to book 30 minutes of my time from between this period. And so students will book, right? So at home, I have a little chart. When they come to exam period, I will say that, okay, I have 9 to 10, 10 to 11. So they will then put down their names and what subject they would like me to coach them on. So that's how I manage. That's because I have children, but when it comes to like family time, I have certain hours that I don't do my work. So for example, Saturday evening, I will just set it aside, bring them out, spend some time with family. But I do make sure that if I do have certain activities or research to do or teaching materials to prepare, I cannot prepare beforehand or use my productive hour early in the morning to do so.
Yeah, thank you.
So that's my method.
I think having children is really a trouble of happiness. Yes, thank you. And it's that Haku. Yeah, what do you think about this question?
I listened all the other comments and opinion or like experience from other speakers from here. And I actually, of course, agree with all those comments. So for example, Niroshini said that, it's not like, 50-50 that you can balance between work and life. There are some times, for example, you have a paper deadline and you need to work, for example, after the office hour, maybe late night, because you have to catch the deadline. But that's not the case all the time. So some other times you can spend more time, you can make up that time that you couldn't spend with your family. Some other times, other days, you can spend time with your family or like with your friends. However, as I mentioned before, that time management, in my opinion, is very important, like, planning ahead for different activities. So for example, I myself, every week, I plan and schedule all the activities that I'm gonna do that particular week. Okay, so meetings with my students, and then any particular study that I want to do, any research work, any teaching preparation, all those things I actually planned for every week, beginning of the week. And that also includes not only I plan for my work, I also plan that, okay, after work, how much time I can then spend with my family and with my friends. And in my opinion, that time management really helps me because I can clearly see that, oh, 3 weeks later, I have a paper deadline. So I start working according to that deadline way before 3 weeks. And then, once that deadline actually approaches, I'm not like very overwhelmed, and, pretty much most of the time I can take care of the situation pretty well. So in addition to all the comments that other speakers mentioned, I would add that time management is like really important in this case if you want to balance between work and life.
Okay, and there's also a last question for you. I want to know, can you very understand you? That is, when you're busy in your work, busy at your work, and you don't have much time for them, can they really understand you?
Yeah. Yes.
Sorry to interrupt. I have another meeting, so I have to go now. So sorry about that. But it was really nice to see all of you. And and thanks for having me. And best of luck to you as well. All right, I'll see you guys.
Really thank you for your experience. Yeah, thank you very much. Yeah, bye-bye. So,
shall I continue?
Yeah.
Okay.
Let's continue. Yeah.
Okay. Yeah. I mean, of course. I mean, if we don't get support from our family members, it's very, difficult. Actually, not only for women,
difficult, yeah.
Even for men, if they don't get support from their partners, from their family members, it's difficult for even them to move forward in their career. But for women, it's extra difficult because we need to take care of our family, kids. If you have kids, you have to take care of them because, even though, like, let's say, your husband or your partner is there, but kids, most of the time, they prefer mom to share different things or ask for something. So obviously for women, this is something like extra responsibilities. I wouldn't say that it is negative. It is actually positive in my opinion that, only women actually can take care of kids in such a way, and then kids are so attached to their mom compared to their dad. But this is also a challenge in terms of their career that they have to take care of both. But as I said, that in that case, definitely support from their partner or husband is really important. And definitely they need to sit together, talk about each other's demand, what they need for their work, and how they can manage this, family life, take care of the kids. For example, they can think that, I can drop kids in the morning to school, and then I can go to my work, and maybe you can actually pick them when the school is over, and that's why I can spend little extra time at work. So there can be some sort of understanding between partners and husband and wife to take care of their family life and support each other.
Yeah, thank you for advice. And that's all my questions. Thank you all very much for your attending, for your valuable experiences, and then for your sharing of them with us. And I wish you a good morning for everyone. Thank you.
Okay, really thanks for your valuable advices and suggestions. I believe that the communication today will be a valuable memory to them, and the end of the meeting will be the beginning of our friendship. Thank you for all the panelists and to women and MONAMI 2020. Let's see you again. Now comes the exciting moment. As a special celebration of the 10th anniversary, we decide to award Best Paper Award to the following 3 papers. The first one is a secure crowdsourcing-based indoor navigation system. The authors are Liang Xie, Zhou Su, and Qi Chao Xu. The second one is distributed spectrum and power allocation for D2D-U networks. The authors are Zhiqun Zhou, Rui Yin, Selemoge Wu, Jian Tao Yuan, and Xianfu Chen. The third paper is Energy Minimization for UAV-enabled video relay system under QoE constraints. The authors are Han Hu, Cheng Zhang, and Jianping An. Thank you very much and congratulations.
Hello everyone, I am a postgraduate student from Shanghai University in China. My name is Liang Xie and my supervisor is Professor Zhou Shu. Today I'm so glad to receive the Best Paper Award of MONAMI. The title of my paper of the Best Paper Award is a secure crowdsourcing based indoor navigation system. The first author is me, the second author and corresponding author is Professor Su, and the third author is Prof. Xu. This work is to apply the crowdsourcing technology to provide high-quality navigation services for mobile users. Besides, the security issues of navigation systems are solved based on offensive and defensive game theory. Here, I would like to thank my supervisor, Professor Su, for his careful guidance, with which I can successfully solve various problems in the research. Next, I would like to thank the organizing committee and chairman of the EAI conference for giving me an outstanding platform to present research results. Although this award is being given to me, it is inseparable from all of support from you, without whom none of this would have been possible. Finally, I would like to say that I'm very happy to be able to award this prestigious award. I believe this award is a high degree of affirmation and support for my work. I will go forward in my future research career.
Hello everyone. First of all, thank you very much for our paper. Distributed spectrum and power location for D2D-U networks can be rated as the best paper of EAI MONAMI 2020. And thanks to the organizing committee and all reviewers for their recognition of our work. I am one of the authors of this paper, Zhou Zhiqun, and am now a graduate student of the College of Information Science and Electronic Engineering, Zhejiang University, China. During my postgraduate period, my research direction has always been the combination of distributed D2D-U communication and machine learning. I have done some work before, but this paper is my most satisfactory work at the moment. I think to some extent it is a consequence of my past learning accumulation, and being rated as the best paper this time is the best recognition and encouragement for me. Special thanks to my supervisor, Professor Ying Rui, for helping me with my research, and thanks to all the co-authors for their help and advice on my work. And also very grateful to other supervisors and students from our laboratory for supporting my work. Regarding this paper, in order to achieve distributed solution as much as possible, that is, D2D-U users decide their communication resources allocation by themselves. We have introduced a model for users to purchase channels, and each user determines the prices of the channels through a neural network. We always believe that distributed solutions are of great significance to the improvement of system performance. And this approach is also applicable to systems such as LTU, V2V, and so on. I think this work is a simple attempt to combine communication resource allocation and machine learning. There should be many points can be improved, and we will continue to work on it. In addition, I want to talk about is that this work was completed during the period of COVID-19, mainly February to May. During that time, most universities had not resumed classes. Thinking about ideas, simulations, writing papers, and online discussions at home are quite novel experiences for me. Of course, they are mainly less convenient experiences. So, I also hope that COVID-19 will pass soon and everyone's life will be back on track. Finally, thank you again for your recognition of our work. I hope that more excellent ideas can meet with you at EAI here, and EAI MONAMI will be better and better. Thank you.
Ladies and gentlemen, Mr. President, and all distinguished guests, my name is Han Hu from Beijing Institute of Technology, China.
I'm overwhelmed with gratitude to have been selected to receive the Best Paper Award of EAI MONAMI 2020. Thank you all so much for being here to share in this occasion. I'm so honored to have my work recognized in this way. First of all, I would like to express my sincere appreciation to the award committee for the recognition and encouragement. It means so much to me that the work I'm so passionate about also resonates with others. This accomplishment is not something that I did alone, and there are many others who deserve to share in this award. I would like to thank Zhang, the co-author of our paper. We have been working together on area of UAV-aided video streaming for more than 5 years. From self-doubt to gradual acceptance, we stick to it together. I would also like to thank Jiangchuan, the team leader of our group. You are my great mentor who have raised me up to a new level of my academic skill and also my life. This year, we are 8 months into the COVID-19 pandemic, and sadly, infections and deaths are accelerating in many parts of the world. Many academic conferences, our conference without exception, have been organized in the form of virtual meeting. I would like to express my sincere thanks to the organization committee for the valuable efforts to guarantee the success of our conference. This year will be difficult and also be a challenge, but if we continue to do our best, we will certainly overcome the COVID-19 and make this year a great success. I wish you and your families a good health and all the best. Thank you all.
Hello, everyone. This has been a wonderful conference. I have enjoyed listening to the talks about fine work being done in mobile communications and computing. It's wonderful for people to learn about excellent research being done in this field. Thank you for that. I always think that attending conferences is not only for studying and exchanging knowledge, but it is more than that. It's a time to make friends and to learn about and come care about each other. I have made new friends here and I have learned much. It is helpful to have a list of all of you with university addresses and emails so we can communicate with each other. In this moment, I would like to share with you some bright things. In next year, we plan to hold this conference, MONAMI 2021, in Chiba, Japan again, and it will be organized by Professor Selimuge Wu from University of Electrocommunications, Japan. With luck, I'm looking forward to seeing you all again, this time in person. Let's end this conference with a promotion video of Chiba.